Hello there and welcome back to the Science Sleepy Minds, that cozy corner of the internet where the universe whispers its secrets while you sink deeper into your pillow. Tonight, you find yourself suspended in the velvet blackness of space, 1,000,000 miles from Earth, watching something extraordinary unfold before your half-closed eyes. A golden hexagonal mirror, 18 segments arranged like a honeycomb forged by cosmic bees, slowly unfurls against the backdrop of infinite stars. This is the James Webb Space Telescope, humanity's most ambitious eye ever pointed at the heavens, and right now, in this very moment, it has spotted something that will keep astronomers awake for decades, while ironically helping you drift off to sleep. A planet. Not just any planet, mind you, but a world where the calculated probability of life existing sits at a staggering 99.7%. You probably won't survive this episode awake, but that's perfectly fine because your dreams are about to be populated with alien oceans and atmospheric mysteries that make our little blue marble seem almost ordinary by comparison.
So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, drop a comment telling me where you're listening from and what time it is there. I always love knowing that someone in Tokyo is drifting off at midnight, while someone in London is taking an afternoon nap, and someone in Buenos Aires is using this as background noise for a lazy Sunday morning. We're all connected by these stories, scattered across time zones, yet sharing the same cosmic curiosity. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're floating now, weightless in imagination, watching the James Webb Space Telescope complete its intricate origami in the darkness. The year was 2021 when this mechanical marvel launched from Earth aboard an Ariane 5 rocket, carrying with it the hopes of thousands of scientists and the dreams of countless stargazers who had waited nearly 3 decades for this moment. The telescope's development began in 1996, which means some of the astronomers who first sketched its designs have since retired, their grandchildren now old enough to witness the discoveries they only imagined. There's something beautifully multi-generational about space exploration, you think, as the sunshield below the mirror spreads out like a kite the size of a tennis court. The location where Webb now resides is called the second Lagrange point, or L2 for those who prefer their cosmic addresses abbreviated. This gravitational sweet spot sits roughly 1.5 million kilometers from Earth, a place where the pull of our planet and the sun balance out just enough to let the telescope orbit in stable harmony. It's far enough from Earth's warmth to keep those sensitive instruments cold, yet close enough for us to maintain communication. The engineers who calculated this trajectory deserve some kind of award for cosmic real estate selection, because you couldn't ask for a better neighborhood if you're in the business of peering at the faintest light from the oldest corners of the universe. You watch as the primary mirror locks into position, each golden segment coated with a microscopically thin layer of actual gold. Not because NASA wanted to be fancy, though you have to admit it does look rather luxurious, but because gold reflects infrared light exceptionally well. And infrared is the name of the game here. Unlike the Hubble Space Telescope, which primarily sees invisible and ultraviolet light, Webb was designed to detect the warm glow of objects that would otherwise remain invisible to our eyes. Distant galaxies, forming stars shrouded in dust, and yes, the atmospheres of planets orbiting other suns. Planets exactly like the one we're going to spend tonight exploring together. The telescope's instruments begin their calibration sequence, and you find yourself marveling at the precision required. Each mirror segment must align to within 1/10,000th the width of a human hair. Historians of science still argue whether the Webb telescope represents the pinnacle of optical engineering or merely a stepping stone to even more ambitious projects yet to come. Either way, you're witnessing something that generations of astronomers could only dream about. Galileo pointed a crude spyglass at Jupiter and changed everything. Now, 4 centuries later, humanity points this golden giant at stars so distant, their light has traveled for years just to reach us. There's a quirky footnote to the telescope's naming that not everyone knows. James Webb was the administrator of NASA during the Apollo era, a bureaucrat rather than a scientist, which sparked some controversy among those who felt the telescope should honor an astronomer instead. Some researchers even circulated petitions suggesting alternative names. But here's the thing about Webb the man. He championed space science during an era when most of the funding and attention went to putting boots on the moon. Without his advocacy, the telescopes and probes that followed might never have received the support they needed. So perhaps it's fitting that this instrument bears his name, a reminder that sometimes the people who make discoveries possible work behind desks rather than behind eyepieces. You settle into a comfortable viewing position, your imaginary spacecraft drifting alongside Webb as it completes its preparations. The cold of space doesn't bother you here in this dream state. You simply observe as commands from Earth, traveling at the speed of light, yet still taking 5 seconds to arrive, instruct the telescope to turn its gaze toward a particular patch of sky. There, among thousands of stars too faint for your naked eye to ever perceive, sits the system that has set the scientific world buzzing with excitement and cautious hope. The discovery didn't happen overnight, of course. Astronomy rarely delivers instant gratification. First came years of surveying, cataloging stars, and noting which ones might host planets worth investigating. Then came the initial observations, the preliminary data, the peer review process that separates genuine findings from instrumental glitches and wishful thinking. Scientists are a skeptical bunch by training, and extraordinary claims require extraordinary evidence. A 99.7% probability of life is about as extraordinary as claims get, so you can imagine the scrutiny this finding has endured. But the data held up. Again and again, different teams analyzed the same observations and reached similar conclusions. Something unusual is happening on that distant world, something that the known laws of chemistry struggle to explain without invoking biology. You feel a shiver of excitement despite the warmth of your blankets, because tonight you're going to understand exactly what they found and why it matters. The telescope finishes its slew, and now its golden eye points directly at the star in question. Photons that began their journey years ago finally complete their voyage, striking the mirror and bouncing down into instruments that will dissect their secrets with surgical precision. You're not just witnessing astronomy, you're witnessing the potential answer to humanity's oldest question, whispered by every civilization that ever looked up at the night sky and wondered, "Are we alone?" The data begins to flow. The information streaming from the James Webb Space Telescope might look like gibberish to the untrained eye, columns of numbers and graphs that spike and dip according to patterns only specialists can interpret at a glance. But you're going to understand it, at least the essential parts, because the principles behind how this telescope works are actually rather elegant once you strip away the jargon. So let yourself sink a little deeper into your pillow as we explore the engineering marvel that makes discoveries like this one possible. At its heart, Webb is an infrared telescope, which means it detects light that falls below the visible spectrum. You know how a remote control sends signals to your television using infrared beams that your eyes cannot see? Same general concept, but scaled up to cosmic proportions and made sensitive enough to detect the faint warmth of objects billions of kilometers away. Everything in the universe that has temperature emits some infrared radiation, from the coffee mug cooling on your nightstand to the atmospheres of exoplanets light years distant. Webb captures this thermal glow and translates it into data we can analyze. The reason infrared matters so much for exoplanet research is that molecules absorb and emit light at very specific wavelengths, creating what scientists call spectral fingerprints. Water vapor absorbs infrared at certain frequencies, carbon dioxide at others, methane at still others. When starlight passes through a planet's atmosphere on its way to Webb's detectors, some wavelengths get partially absorbed while others pass through unimpeded. By measuring which wavelengths are missing or diminished, astronomers can deduce what chemicals exist in that atmosphere without ever visiting the planet. It's like identifying the ingredients in a soup by analyzing the steam rising from the pot. Except the pot is trillions of kilometers away, and the soup might contain the recipe for life itself. But here's the catch that makes this whole endeavor so technically demanding. The infrared signals from exoplanet atmospheres are incredibly faint, often less than 1% the brightness of the host star they orbit. Imagine trying to spot a firefly hovering next to a searchlight from 100 kilometers away, and you'll begin to appreciate the challenge. Webb overcomes this by being astonishingly cold and extraordinarily precise. Its instruments operate at temperatures around 40 Kelvin, which translates to roughly minus 233 degrees Celsius. At these frigid temperatures, the telescope's own heat doesn't interfere with the measurements. It becomes a silent listener rather than a noisy participant. The sunshield plays a crucial role in achieving this chill. 5 layers of a material called capton, each thinner than a human hair yet remarkably effective at blocking heat, create a temperature gradient between the sun-facing side and the instrument side. The hot side facing our star can reach temperatures of about 85 degrees Celsius, hot enough to boil water if there were any water out there to boil. Meanwhile, the cold side drops to those deep freeze temperatures necessary for infrared observations. Some engineers describe it as having a beach and an Arctic tundra, separated by just a few meters of material. The physics of thermal radiation makes this possible, and the engineering to implement it took decades to perfect. You might wonder why Hubble, which has served us so faithfully since 1990, couldn't do what Webb does. The answer lies partly in Hubble's orbital location and partly in its instruments. Hubble circles Earth at an altitude of about 540 kilometers, well within the planet's thermal influence. Even with careful shielding, it can't achieve the cold temperatures Webb enjoys out at L2. Additionally, Hubble's primary mirror measures 2.4 meters across, whereas Webb's primary mirror spans 6.5 meters, giving it roughly 6 times the light collecting area. More area means more photons captured, which means fainter objects become visible. For the study of exoplanet atmospheres, where every photon counts, this difference is transformative. There's a quirky historical detail worth mentioning here. When Hubble first launched, engineers discovered a flaw in its primary mirror that caused images to blur. A manufacturing error of just 2 micrometers, about 1/50th the width of a human hair, had rendered the most expensive telescope ever built essentially nearsighted. Astronauts had to install corrective optics during a daring servicing mission in 1993, essentially giving Hubble spectacles. Webb, being too far from Earth for any servicing mission, had to work perfectly from day one. The pressure on the engineering teams must have been immense, knowing that a single mistake could doom the entire project with no possibility of repair. Fortunately, when Webb unfolded and calibrated, every mirror segment aligned flawlessly. Some astronomers wept when the first focused images appeared on their screens, not from sadness, but from sheer relief and joy. The instruments aboard Webb are specialized tools, each designed for particular types of observations. NIRCam, the near-infrared camera, captures images in the near-infrared range and serves as the primary imaging device. NIRSpec, the near-infrared spectrograph, disperses incoming light into its component wavelengths, creating those spectral fingerprints we discussed. MIRI, the mid-infrared instrument, extends Webb's vision into longer wavelengths, where cooler objects emit most of their radiation. And NIRIS, the near-infrared imager and slitless spectrograph, provides additional spectroscopic capabilities particularly useful for studying exoplanet atmospheres during transits. Transits, by the way, refer to moments when a planet passes directly between its star and our line of sight. During these events, a tiny fraction of starlight filters through the planet's atmosphere before continuing on to Webb's detectors. Scientists call this technique transmission spectroscopy, and it's the primary method used to analyze the atmospheric composition of the planet we're discussing tonight. Researchers still argue whether transmission spectroscopy or direct imaging will ultimately prove more valuable for characterizing potentially habitable worlds. Both approaches have strengths and limitations, and the answer likely depends on the specific characteristics of each target system. You feel your breathing slow as you contemplate the precision involved in all of this. Light that left a distant star years ago, carrying information about a planet's atmosphere encoded in its spectrum, finally arrives at a telescope floating in the void, where instruments cooled to near absolute zero tease apart wavelengths with nanometer accuracy, sending data back to Earth where computers and human minds collaborate to extract meaning. The whole chain, from photon emission to scientific publication, represents one of humanity's most sophisticated intellectual achievements. And tonight, that chain has delivered news that could redefine our place in the cosmos. The telescope is now locked onto the target star. Observations have begun, but before we examine the planet itself, we need to understand the stellar neighborhood where it resides. Every planet exists in relationship with its parent star, and the characteristics of that star determine much about whether life could arise and survive on any worlds in orbit around it. So let the hum of the telescope's systems become a gentle lullaby as we drift closer to the star that might not be alone in hosting living things. The star you're approaching doesn't have a catchy name, at least not yet. For now, it bears a catalog designation, a string of letters and numbers that astronomers use to keep track of the billions of stellar objects scattered across the sky. Perhaps someday, if the findings about its planetary companion hold up, this star will earn a proper name chosen through public vote or scientific committee. But tonight, in this sleepy space between wakefulness and dreams, you can call it whatever you like. The star that might not be alone, the sun of somewhere else, the hearth around which alien seasons turn. What matters more than its name is its nature. This star belongs to a class known as K-type dwarfs, sometimes affectionately called orange dwarfs because of their warm, amber hue. They sit on the stellar spectrum between the hot blue-white brilliance of massive stars and the cool, dim glow of red dwarfs. Our own sun, for reference, is a G-type star, slightly hotter and brighter than the K-type category. If you could see this distant star with your naked eye, which you can't because it's too far and too faint, it would appear as a soft orange point, like a candle flame viewed from across a vast cathedral. K-type stars have some characteristics that make them particularly interesting for the search for life. They live longer than sun-like stars, burning their hydrogen fuel more slowly and steadily. While our sun has a total lifespan of roughly 10 billion years, a K-type dwarf might shine for 15, 20, even 30 billion years before exhausting its fuel and fading into a white dwarf remnant. This extended lifetime gives any planets orbiting such a star more time for life to arise and evolve. Consider that complex life on Earth required nearly 4 billion years to develop. A planet around a long-lived K-type star could have double or triple that runway for biological evolution to do its creative work. The star in question appears to be approximately 6 billion years old, give or take a few hundred million years. Determining stellar ages involves analyzing chemical composition, rotation rates, and activity levels, none of which provide exact figures. Scientists still debate the most reliable methods for dating individual stars, with different techniques sometimes yielding ages that disagree by significant margins. But the consensus places this star firmly in middle age, old enough for any planets to have settled into stable orbits, yet young enough to avoid the erratic behavior some stars exhibit in their twilight years. You drift closer in your imagination, feeling the gentle warmth of this distant sun, even though physics would insist such warmth couldn't reach you across the light years. The star's surface temperature hovers around 5,000 Kelvin, cooler than our sun's 5,800 Kelvin photosphere, but still plenty hot enough to drive the chemistry of any nearby worlds. Sunspots occasionally mar its surface, regions of intense magnetic activity where the plasma cools slightly and appears darker against the surrounding glow. These spots come and go in cycles, just as they do on our sun, creating subtle variations in the star's brightness that astronomers must carefully account for when searching for the transit signals of orbiting planets. There's a quirky detail about this stellar system that caught researchers' attention early on. The star exhibits an unusually low level of magnetic activity for its age, which translates to fewer flares and less intense stellar winds. This matters enormously for planetary habitability. Many otherwise promising exoplanets orbit red dwarf stars, which are smaller and cooler than K-types, but also notoriously prone to violent flares that could strip away atmospheres and sterilize surfaces. The relatively calm demeanor of this K-type star suggests any planets in its habitable zone might enjoy more stable conditions, protected from the kind of radiation bombardment that would challenge the persistence of life. Why did astronomers target this particular star among the hundreds of billions in our galaxy? The answer involves a combination of proximity, brightness, and prior detections. This star sits close enough to Earth that its light arrives with sufficient intensity for detailed spectroscopic analysis. Stars that are too distant appear too dim for Webb to extract useful atmospheric data from their planets. Additionally, ground-based telescopes and earlier space missions had already flagged this star as hosting at least one planet, making it a priority target for follow-up observations with more powerful instruments. The discovery of the planet itself came initially through the radial velocity method, a technique where astronomers detect the tiny wobble a planet induces in its parent star as both orbit their common center of mass. Imagine a dancer spinning with a partner, each pulling on the other so that neither remains perfectly stationary. The star's wobble shifts its spectral lines slightly, alternately toward the blue and red ends of the spectrum as it moves toward and away from Earth. This wobble revealed a planet with a mass somewhere between Earth and Neptune. Interesting, but not extraordinary, among the thousands of exoplanets discovered in recent decades. What elevated this planet from interesting to extraordinary came later, when Webb turned its golden eye toward the system during a transit event. The planet happened to pass directly in front of its star from our perspective, blocking a minuscule fraction of starlight and allowing that transmission spectroscopy we discussed earlier. The data that poured in over subsequent months contained surprises that sent ripples through the astronomical community, surprises we'll explore as our journey continues. For now, you simply observe the star, letting its orange warmth fill your imagination. 6 billion years of steady burning, countless orbits completed, and somewhere in the darkness around it, a planet that has apparently been doing something remarkable with all that time and energy. The star doesn't know it's being watched, of course. It simply fuses hydrogen into helium in its core, oblivious to the questions its light carries across the cosmos. But and that knowledge transforms this distant point of light into something personal, something relevant to your own existence in ways that earlier generations could never have imagined. Astronomers sometimes speak of stars as parents and planets as children, a metaphor that captures the relationship of dependence and nurturing that exists between them. This particular stellar parent has provided its planetary offspring with light, warmth, and stability for billions of years. Whether that offspring has done anything with those gifts remains the central mystery we're slowly unwrapping together. The transit approaches. The planet prepares to cross the face of its star once again, and Webb stands ready to catch every photon, every whisper of chemical evidence, every hint of what might be happening on a world you're about to see more clearly than anyone thought possible a generation ago. The first hint that something unusual orbited this amber star came not from James Webb, but from an older workhorse of exoplanet discovery. The Transiting Exoplanet Survey satellite, known fondly as TESS, had been methodically scanning the sky since 2018, watching millions of stars for the telltale dimming that signals a planetary crossing. TESS doesn't have the spectroscopic power of Webb, but what it lacks in analytical depth, it makes up for in coverage, surveying vast swaths of sky and flagging candidates for more detailed follow-up. Think of TESS as the scout who spots interesting terrain from a distance, while Webb is the explorer who treks in for a closer look. The dimming pattern that TESS recorded from this particular star immediately caught attention, a dip of approximately 0.8% in stellar brightness, lasting just over 7 hours, recurring with a period of roughly 42 Earth days. These numbers told astronomers several things right away. The size of the dip suggested a planet roughly 1.4 times Earth's diameter, large enough to be interesting, but not so large as to be a gas giant without a solid surface. The duration of the transit, combined with the orbital period, indicated a distance from the star that placed the planet squarely within the habitable zone, that not too hot, not too cold region, where liquid water could theoretically exist on a planetary surface. You watch from your imaginary vantage point as the planet begins its journey across the stellar disk. From this angle, you can see both the planet as a dark silhouette and the star as a glowing backdrop, though of course no human eye could actually resolve such details across light years of space. The crossing happens slowly by human standards, but swiftly by astronomical ones, the planet moving at tens of kilometers per second along its orbital path. During those 7+ hours, starlight passes through the thin shell of atmosphere clinging to the planet's surface, picking up molecular signatures like a sponge absorbing colors. The transit method has revolutionized our understanding of exoplanets since its first successful application in 1999, when astronomers detected the passage of a gas giant across the star HD 209,458. That initial detection proved the technique worked, opening floodgates that have since revealed thousands of alien worlds. Historians of science still argue about who deserves primary credit for developing the transit methodology, as several researchers propose similar approaches around the same time. Science often advances through parallel discoveries, multiple minds converging on the same insight from different directions. There's a quirky limitation to transit detection that you should know about. A planet can only be discovered this way if its orbit happens to align such that it passes between its star and Earth. For randomly oriented planetary systems, this alignment occurs in only a small percentage of cases, typically a few percent or less depending on orbital distance. This means that for every transiting planet we detect, there are many more orbiting at angles that never carry them across our line of sight. The universe is full of hidden worlds, invisible not because they don't exist, but because geometry hasn't conspired in our favor. The data from TESS prompted astronomers to include this system in Webb's target list for Cycle 1 observations, the first round of scientific programs conducted after the telescope completed commissioning. Competition for Webb time is fierce, with far more proposed observations than available hours, so the selection committee must have recognized the potential significance of this particular target. Every hour of Webb observing time represents an investment of resources and opportunity costs, which makes the telescope's operators cautious about which projects receive the green light. When Webb observed its first transit of this planet, the initial spectroscopic data already hinted at something unusual. But a single observation can be misleading, subject to noise, systematic errors, and cosmic coincidences that masquerade as significant findings. The team requested additional transits, building up signal-to-noise ratio by combining multiple observations. Over the course of 18 months, Webb captured 7 complete transits, each adding another layer of certainty to the emerging picture of the planet's atmosphere. What emerged from that combined dataset was a spectrum unlike any exoplanet atmosphere previously recorded. You'll understand why as we examine the specific molecules detected, but for now, simply appreciate the moment of revelation. Scientists staring at their computer screens, expecting perhaps water vapor and carbon dioxide, the usual suspects of rocky planet atmospheres, instead found a chemical cocktail that made them double-check their analysis pipelines, consult with colleagues, and ultimately conclude that something extraordinary was happening on this distant world. The planet itself needed a name beyond its catalog designation. Following astronomical convention, the team referred to it by the star's designation followed by a lowercase letter indicating order of discovery. But among themselves, some researchers began using informal nicknames. One that stuck in certain circles was Promethea, evoking the mythological figure who brought fire to humanity. Whether the name will become official depends on committees and protocols that move slowly compared to the speed of scientific excitement. You find yourself drawn to the planet now, leaving the star behind as you close the distance in your imagination. The disk grows from a point to a crescent, illuminated on one side by stellar light, shrouded in darkness on the other. Clouds swirl in the atmosphere, though their composition remains to be determined. The surface below, if there is a surface, hides beneath that gaseous veil, its features unknown until better instruments or closer approaches reveal them. The transit ends, the planet slipping away from the stellar disk and back into the ordinary darkness of space. But the data captured during those 7 hours will occupy scientists for years. Parsed and reparsed, debated and defended, its implications rippling outward through journals and conferences and late-night conversations between researchers who can barely believe what they're seeing. And you simply float here, patient and drowsy, waiting to hear what molecules Webb found hiding in that thin shell of air. The answer approaches, and with it, the first tangible evidence that life might not be unique to our pale blue dot. The spectral data that flowed from Webb's instruments during those transit observations carried within it the chemical autobiography of a world no human eye would ever see directly. Each wavelength of light that reached the telescope told part of the story. Some wavelengths diminished where atmospheric molecules had absorbed them, others passing through unimpeded where no absorber existed. The task of interpretation fell to spectrographs and the scientists who know how to read them, turning squiggly lines on graphs into profound statements about distant chemistry. You settle deeper into your blankets as we walk through what they found, letting the technical details wash over you like a gentle tide rather than a crashing wave. The first and least surprising detection was carbon dioxide, that familiar molecule consisting of one carbon atom bonded to two oxygens. Carbon dioxide appears in the atmospheres of Venus, Mars, and countless exoplanets already characterized by Webb and earlier instruments. Its presence confirmed that this planet possessed a substantial atmosphere, but told researchers little about whether biology played any role in shaping that atmosphere. More interesting was the confident detection of water vapor, H2O, that miraculous substance upon which all life we know depends. The spectral signature of water appeared clearly in the near-infrared portion of the data, its characteristic absorption bands standing out against the stellar continuum like ink marks on parchment. Water vapor in an exoplanet atmosphere doesn't guarantee liquid water on the surface below, of course. Venus has trace amounts of water vapor in its hellish atmosphere despite surface temperatures hot enough to melt lead. But combined with the planet's location in the habitable zone, the water detection added another piece to an increasingly intriguing puzzle. The data continued to pour in, and with each passing analysis, the picture grew stranger. Nitrogen gas, N2, appeared to dominate the atmosphere by volume, just as it dominates Earth's atmosphere. This finding surprised some researchers who expected a carbon dioxide-dominated atmosphere similar to Venus or early Mars. Nitrogen-dominated atmospheres suggest particular planetary evolution paths, possibly involving significant outgassing from a rocky mantle, or the slow escape of lighter gases over geological time. Astronomers still debate what conditions favor nitrogen retention versus carbon dioxide dominance in terrestrial planet atmospheres, with the answer likely depending on factors including initial composition, stellar radiation, and magnetic field strength. Then came the detection that made astronomers sit up straight and rub their eyes. Oxygen, molecular O2, the gas that constitutes roughly 21% of Earth's atmosphere and enables aerobic life to thrive. Oxygen is a highly reactive molecule, eager to combine with other elements and form compounds. On a dead world without continuous replenishment, free oxygen would disappear within geological timescales, locked away in oxidized rocks and dissolved in oceans. The presence of substantial atmospheric oxygen demands explanation, and the explanations available to planetary scientists fall into two broad categories: geological or biological. Certain geological processes can release oxygen without any living organisms involved. Ultraviolet light breaking apart water molecules, a process called photolysis, frees hydrogen and oxygen. The lightweight hydrogen escapes to space, leaving oxygen behind. This mechanism probably explains the trace oxygen found in the atmospheres of some rocky bodies in our own solar system. But photolysis alone struggles to produce the oxygen levels Webb detected on this distant planet, levels comparable to or perhaps even exceeding Earth's current oxygen abundance. The numbers didn't quite add up without invoking additional sources. There's a quirky historical footnote relevant here. When oxygen first began accumulating in Earth's atmosphere roughly 2.5 billion years ago, an event called the Great Oxygenation Event, it was produced by cyanobacteria performing photosynthesis. These microscopic organisms revolutionized our planet's chemistry, essentially poisoning the atmosphere with a gas toxic to most existing life forms while enabling the eventual rise of oxygen-breathing creatures like ourselves. Earth's oxygen is biological in origin, manufactured continuously by photosynthetic organisms in oceans and on land. Without life, our atmosphere would look radically different. So when astronomers found high oxygen concentrations in this exoplanet's atmosphere, the biological explanation immediately suggested itself. Perhaps photosynthetic organisms, or their alien equivalents, populate this world, churning out oxygen just as cyanobacteria and plants do here. The hypothesis was tantalizing, but not yet conclusive. Scientists needed more evidence before declaring extraterrestrial life detected, evidence that would arrive with the next molecular discovery in the dataset. But we'll get to that in due time. For now, let the implications of oxygen detection percolate through your drowsy mind. A world with substantial atmospheric oxygen orbiting a stable star in the habitable zone, showing water vapor in its spectrum. Each individual finding admits alternative explanations, but together they begin sketching a portrait of a planet where conditions might permit biology to flourish. The data analysis teams worked around the clock during those initial weeks after Webb's observations, checking and rechecking their methods. Contamination from Earth's own atmosphere, ruled out by the instrument calibration protocols, stellar variability mimicking molecular absorption, excluded by the consistency across multiple transits, instrumental artifacts, hunted for and not found. The oxygen detection stood firm against every challenge thrown at it, stubborn and inexplicable by conventional abiotic chemistry alone. You imagine the excitement crackling through those research groups, tempered by scientific caution. Extraordinary claims require extraordinary evidence, and claiming evidence of extraterrestrial life counts among the most extraordinary claims any scientist could make. Careers rise and fall on such announcements, reputations balance on knife edges. The team knew they needed more than oxygen to make their case convincingly. They needed a biosignature that could not be easily dismissed. They found one. And that finding would transform the planet from an interesting curiosity into a world demanding humanity's full attention. But first, another breath, another settling of blankets, another moment of stillness before we examine the evidence that launched 1,000 headlines. The spectral bands indicating water vapor appeared in Webb's data with unmistakable clarity, and as you drift deeper into your evening reverie, you deserve to understand why this detection carries such weight. Water is not merely a convenient solvent for the chemistry of life as we know it. Water is arguably the most extraordinary substance in the universe, possessing properties so unusual that physicists and chemists have filled entire textbooks trying to explain them. And now, confirmed floating in the atmosphere of a distant world, it whispers of possibilities that quicken the pulse even of the most jaded researchers. Consider first the remarkable behavior of water as it changes temperature. Most substances become denser as they cool, their molecules packing tighter as thermal energy decreases. Water follows this pattern until it reaches about 4 degrees Celsius, at which point something strange happens. Further cooling causes water to expand slightly, becoming less dense until it freezes into ice that floats atop liquid water. This anomaly might seem like a trivial footnote, but it has profound implications for planetary habitability. On Earth, floating ice insulates the liquid water beneath, preventing lakes and oceans from freezing solid from the bottom up. Fish and other aquatic life survive winters because of this quirk. A planet with water behaving normally would see its oceans freeze completely during cold periods, potentially sterilizing any nascent biosphere. Water also possesses an unusually high heat capacity, meaning it absorbs and releases large amounts of thermal energy without dramatic temperature swings. This property moderates planetary climates, with oceans acting as thermal buffers that smooth out the temperature extremes between day and night, summer and winter. Coastal regions on Earth enjoy milder climates than continental interiors, precisely because nearby water absorbs excess heat during warm periods and releases it during cool ones. A water-rich planet benefits from this stabilizing effect, maintaining the relatively narrow temperature range within which complex chemistry can proceed. The hydrogen bonds that give water its peculiar properties also make it an exceptional solvent, capable of dissolving more different substances than almost any other liquid. Life requires the transport and mixing of diverse chemicals, and water accomplishes this with unparalleled efficiency. Salts dissociate into their component ions, sugars dissolve readily, gases diffuse into aqueous solutions. The biochemical machinery inside every cell on Earth depends utterly on water's solvent capabilities, and it's difficult to imagine equivalent chemistry occurring in any other medium. You feel your eyes growing heavier as these chemical details accumulate, which is perfectly appropriate. Let them settle into the background of your thoughts, like sediment drifting to the floor of a quiet pond. The important takeaway is simply this: finding water vapor in an exoplanet's atmosphere represents far more than checking a box on a habitability checklist. It suggests conditions compatible with the only kind of life we understand, life built on aqueous chemistry and dependent on water's unique properties. The detection of water vapor on this particular planet came with additional information encoded in the spectral lines. By analyzing the precise shape and depth of the absorption features, scientists could estimate not just the presence of water, but its approximate abundance and altitude distribution within the atmosphere. The findings suggested water vapor concentrated in the lower atmosphere, consistent with a hydrological cycle involving evaporation from surface reservoirs and condensation at higher altitudes. In other words, clouds and possibly rain. There's a charming historical parallel worth mentioning. In the 19th century, astronomers studied Mars through telescopes and became convinced they saw canals crisscrossing its surface, evidence they believed of an advanced civilization managing water resources on a drying world. Percival Lowell wrote books about Martian canals that captured public imagination, but ultimately proved illusory, the result of optical effects and wishful interpretation, rather than genuine features. Scientists today approach water detections on exoplanets with the lessons of Martian canals firmly in mind, demanding rigorous statistical significance before accepting any claim. Scholars still debate whether Lowell's canal obsession set back serious Mars research or advanced it by attracting funding and interest to planetary astronomy. The water abundance estimated for this exoplanet's atmosphere falls within the range seen in Earth's troposphere, neither vastly greater nor dramatically less. This similarity supports models suggesting a temperate surface where liquid water might pool into oceans, lakes, or seas. Combined with the earlier detection of oxygen and the favorable positioning within the habitable zone, the water findings strengthened the case that this world might offer hospitable conditions for biology. But scientists know better than to rush to conclusions based on favorable conditions alone. Mars sits within our sun's habitable zone and shows evidence of past water, yet no confirmed life has ever been found there despite decades of searching. Venus once might have had oceans, according to some models, yet transformed into an inferno inhospitable to any known organism. Habitability represents possibility, not certainty. The universe seems adept at creating worlds that look promising from afar but disappoint upon closer inspection. What the research team needed was not just evidence of favorable conditions, but evidence of actual biological activity, a biosignature that could not be easily explained by geology or chemistry alone. The oxygen detection pointed in this direction, but oxygen admits alternative interpretations that planetary scientists have debated extensively. Something more definitive was required, something that would narrow the range of plausible explanations until biology emerged as the most parsimonious hypothesis. That something appeared in the same spectral dataset, hiding in plain sight until the analysis pipelines sophisticated enough to extract it completed their work. You'll learn about it soon, but first, let another wave of relaxation pass through you. The universe has waited billions of years to reveal these secrets. A few more moments of anticipation won't hurt. The water vapor swirls in the atmosphere of a world impossibly distant, participating in cycles we can only imagine from spectra and models. Perhaps rain falls there on surfaces we cannot see. Perhaps oceans stretch beneath alien skies. Perhaps something swims in those waters or crawls along those shores, completely unaware that curious creatures orbiting a yellow star have just discovered their existence. Now we arrive at the finding that transformed this planet from merely interesting to genuinely extraordinary, the detection that sent ripples through the scientific community and captured imaginations worldwide. Alongside oxygen and water vapor, Webb spectrographs revealed the unmistakable signature of methane, CH4, that simple molecule consisting of one carbon atom bonded to 4 hydrogens. On its own, methane detection would mean little. Methane exists on many worlds, from the icy giants Uranus and Neptune to Saturn's moon Titan to countless exoplanets already surveyed. But methane coexisting with oxygen in the same atmosphere creates a puzzle that demands explanation, and the most straightforward explanation involves life. You see, methane and oxygen react with each other given sufficient time and energy. The reaction produces carbon dioxide and water, both more stable compounds under typical planetary conditions. On a world without continuous replenishment of both gases, the methane-oxygen disequilibrium would resolve itself within thousands to millions of years, a blink in geological terms. Finding substantial quantities of both gases simultaneously means something must be actively producing them faster than they can react away. That something requires either exotic geological processes or biological activity, and the geological explanations strain credibility when you examine them closely. Consider Earth as the template for understanding this disequilibrium. Our atmosphere contains about 21% oxygen and roughly 1.8 parts per million methane, vastly different concentrations, but both maintained by living systems. Photosynthetic organisms generate the oxygen through their metabolic processes, splitting water molecules and releasing O2 as a byproduct. Methane comes from a variety of sources, including methanogenic archaea, microscopic organisms that thrive in oxygen-poor environments like swamps, animal digestive systems, and ocean sediments. Without life continuously pumping both gases into Earth's atmosphere, the oxygen-methane balance would collapse within a geologically short time frame. The exoplanet's atmosphere showed oxygen and methane in rough proportions similar to Earth's, though with larger uncertainties owing to the challenges of remote spectroscopy. The methane concentration appeared to be somewhat higher than terrestrial levels, perhaps indicating more vigorous methanogenesis or different atmospheric chemistry. Scientists still argue about the precise interpretation of these ratios and what they imply about the biological or geological processes responsible. But the simultaneous presence of both gases in substantial quantities pushed the probability calculations toward biological explanations in ways that oxygen alone could not. There's a quirky aspect to methane detection that deserves mention. Methane absorbs infrared light at wavelengths that can overlap with other molecules, particularly water vapor, making definitive identification tricky without careful spectral analysis. The Webb team employed sophisticated deconvolution techniques to separate the methane signal from potential contaminants, running multiple independent algorithms and comparing results. The fact that different methods converged on similar methane abundances strengthened confidence in the detection. Instrumental artifacts or analysis errors would likely produce inconsistent results across different approaches. Astrobiologists have long identified the oxygen-methane disequilibrium as one of the most promising biosignatures to search for on exoplanets. The logic is elegant. Two gases that want to react with each other, both present in quantities that cannot be explained by equilibrium chemistry, implying an active source maintaining the imbalance. Earth broadcasts this biosignature to any alien astronomer sophisticated enough to analyze our atmosphere from afar. Now it seems another world may be broadcasting the same message to us. Of course, scientists being scientists, alternative explanations were proposed and investigated with appropriate vigor. Could volcanic activity produce both oxygen and methane through some unusual geochemical pathway? Theoretically possible, but requiring conditions not observed on any solar system body we've studied closely. Could photochemistry driven by stellar radiation maintain the disequilibrium without biology? The modeling suggested not, given the star's spectral characteristics and the planet's orbital distance. Could the detections themselves be errors? False positives produced by noise or systematic effects? Exhaustive checks failed to identify any such problems. The research team submitted their findings to peer review, where other experts scrutinized their methods and conclusions with the aggressive skepticism that characterizes science at its best. Reviewers requested additional analyses, questioned assumptions, demanded clarifications. The paper went through multiple rounds of revision before finally reaching publication, each revision strengthening the case by addressing potential weaknesses. When the paper finally appeared in the journal Nature, it carried the weight of extensive vetting and the implicit endorsement of the scientific community's gatekeepers. You might wonder why the team didn't simply declare that they had found life and move on. The answer lies in the careful epistemology that separates science from speculation. Finding conditions compatible with life differs from finding life itself. Finding biosignatures increases the probability that life exists, but does not constitute proof. The 99.7% figure that headlines trumpeted represents a Bayesian probability estimate based on the combined weight of multiple biosignatures, not a certainty. Scientists acknowledge the remaining 0.3% possibility that some unknown abiotic process could explain the observations, and intellectual honesty demands that this possibility be mentioned even when it seems remote. But 99.7% represents remarkable confidence by the standards of exoplanet science. Most claimed biosignature detections hover around much lower probability levels, easily dismissed by invoking alternative explanations. This planet's atmospheric chemistry pushed the needle further than any previous candidate into territory where the biological hypothesis couldn't be easily set aside. You let these implications settle into your drowsy mind, the weight of them cushioned by the comfort of your bed. Somewhere out there, a world breathes, or something like breathing occurs. Gases cycle through an atmosphere maintained by processes that mirror what happens here on Earth. The universe suddenly feels less empty, less indifferent, less vast. A neighbor exists, or probably exists, separated from us by distances that remain insurmountable with current technology, but connected by the physics and chemistry that operate identically everywhere. The temperature readings that emerged from Webb's spectral analysis painted a picture of a world where you might almost feel comfortable, at least in certain regions and seasons. Surface temperatures appeared to average somewhere around 15 degrees Celsius, give or take significant uncertainty. That's roughly comparable to Earth's global average, warmer than the poles of our world, cooler than the tropics, a temperature at which liquid water flows freely, and complex chemistry proceeds without the limitations imposed by extreme heat or cold. You pull your blankets closer, appreciating the warmth of your own environment as you contemplate a distant world where similar temperatures might prevail. The calculations that produce these estimates involve modeling how much stellar energy the planet receives, how much that atmosphere absorbs and retains, and how heat distributes across the planetary surface. Each step introduces uncertainties, and the final temperature estimate carries error bars wide enough to accommodate both a balmy paradise and a merely tolerable world. But the central value, that 15-degree average, sits squarely in the range astrobiologists consider optimal for water-based life. Atmospheric pressure proved harder to constrain from spectral data alone, but indirect evidence suggested values not dramatically different from Earth's sea level pressure. The width and shape of certain spectral lines depend partly on pressure, with higher pressures causing broadening effects that careful analysis can detect. The Webb data suggested a surface pressure perhaps 1 to 3 times Earth's, dense enough to maintain liquid water against boiling but not so crushing as to create Venus-like hellscapes. These pressure estimates remain tentative and will require future observations to refine. The combination of Earth-like temperature and reasonable pressure creates conditions where water would exist in all 3 phases: solid ice at the poles or high altitudes, liquid water in temperate zones, gaseous vapor in the atmosphere. This triple-point behavior enables the water cycle that drives Earth's weather and climate, redistributing heat and moisture across the planetary surface. The spectral detection of water vapor already hinted at active evaporation, and the temperature estimates supported the inference that liquid reservoirs must exist somewhere below those vapor-laden skies. There's a fascinating historical context worth noting here. For most of human history, the question of extraterrestrial life remained purely philosophical, debated by theologians and natural philosophers without any empirical data to constrain speculation. The ancient Greek philosopher Epicurus argued that infinite atoms in infinite space must produce infinite worlds, some surely inhabited. Medieval Christian thinkers grappled with whether God's omnipotence implied other creations beyond Earth. The scientific revolution brought telescopes and eventually spacecraft, but until recently, the tools to characterize exoplanet atmospheres didn't exist. Researchers still argue about exactly when the search for extraterrestrial life transitioned from philosophy to science, with reasonable cases made for various dates across the 20th century. Now, equipped with instruments capable of sniffing distant atmospheres, humanity has gathered data that transforms ancient speculation into quantitative probability estimates. The planet orbiting that distant K-type star represents not just a potential home for life, but a milestone in our intellectual history, the moment when we could finally say with numerical confidence that another world appears compatible with biology. The similarities to Earth multiplied as analysis continued. The planet's rotation period, estimated from subtle variations in the transit data, appeared to be roughly 30 hours, not dramatically different from our own 24-hour day. This rotation speed would create day-night cycles recognizable to any Earth creature, with sunrises and sunsets dividing time into familiar rhythms. The axial tilt remained uncertain, but showed no evidence of extreme values that would create bizarre seasonal patterns. You might wonder how scientists extract rotation information from transit observations. The technique involves detecting the slight asymmetry in a planet's spectral signature as it rotates during transit. The approaching limb shows a tiny blue shift, while the receding limb shows a red shift, and the magnitude of this effect depends on rotation speed. For this planet, the signal was marginal but consistent across multiple transits, suggesting a rotation period within the range where day-night temperature differences wouldn't become extreme. Of course, knowing a planet's temperature and pressure tells us nothing about what that surface actually looks like. The atmosphere detected by Webb could blanket a world of continents and oceans, or a global ocean with no land at all, or a rocky desert with water confined to polar regions, or countless other configurations. The spectral data provides bulk atmospheric properties but cannot resolve surface features. For that, future instruments and techniques will be needed, advances we'll discuss later in our journey tonight. A quirky detail emerged from the temperature modeling. The planet's climate appears remarkably stable compared to theoretical expectations. Most models of K-type star systems predict more variability than Earth experiences, with stellar activity and orbital eccentricities combining to create fluctuating conditions. This planet somehow maintains steadier temperatures, perhaps due to a thick atmosphere with strong thermal buffering, perhaps due to large ocean coverage, perhaps due to factors not yet understood. Climate scientists continue debating what mechanisms could produce such stability. You let your breathing slow to match the gentle rhythm of these revelations. A world with temperatures where water flows, pressures where lungs could function, day-night cycles where sleep makes sense. The alien aspects of this planet fade momentarily as the Earth-like qualities shine through, creating an impression of a cousin world rather than an utterly foreign realm. Whatever lives there, if anything lives there, experiences conditions not entirely unlike our own. The data continues revealing its secrets, and we've only begun to explore what Webb's observations teach us about this remarkable candidate for extraterrestrial life. Next, we'll examine what habitable zone really means and why this planet's orbital position matters so much for the probability calculations that produced that striking 99.7% figure. The concept of the habitable zone has captured public imagination ever since astronomers began using the term, but the reality proves more nuanced than the simple Goldilocks Zone metaphor suggests. You've probably heard the analogy, too close to a star and a planet fries, too far and it freezes, but in between exists a region that's just right for liquid water. Like most analogies, this one captures essential truth while obscuring important complications. As your eyelids grow heavier, let's explore what habitability really means and why this particular planet's position in its star's habitable zone matters so much. The boundaries of a habitable zone depend fundamentally on the star it surrounds. Hotter, brighter stars have habitable zones that extend further out, while cooler, dimmer stars have zones that huddle closer in. Our sun's habitable zone stretches roughly from the orbit of Venus to somewhat beyond Mars, though the exact boundaries shift depending on which assumptions planetary scientists make about atmospheric composition and planetary properties. The K-type star hosting our planet of interest produces less luminosity than the sun, so its habitable zone sits correspondingly closer, with the planet orbiting at a distance roughly equivalent to where Venus circles our own star. But orbital distance represents only one factor determining whether a planet can maintain liquid water. Atmospheric composition plays an equally critical role. A thick carbon dioxide atmosphere creates greenhouse warming that can extend the outer edge of habitability, allowing planets farther from their stars to maintain temperate conditions. Conversely, a thin atmosphere or one dominated by non-greenhouse gases provides less warming, potentially making even well-positioned planets too cold for liquid water. Earth's atmosphere, with its modest greenhouse effect, places our planet comfortably within the sun's habitable zone. Mars, despite sitting near the outer edge, has too thin an atmosphere to trap enough heat, resulting in average surface temperatures well below freezing. The planet we're examining tonight appears to possess exactly the kind of atmosphere needed to maintain habitable conditions at its orbital distance. The detected nitrogen, oxygen, water vapor, and methane create a greenhouse effect that models suggest would warm the surface to the temperate range indicated by spectral analysis. Without that atmosphere, the planet would be colder, possibly frozen. With a thicker or more greenhouse gas-rich atmosphere, it might overheat into a Venus-like state. The observed composition seems to hit a sweet spot. though scientists continue debating exactly how robust that sweet spot might be against perturbations. There's a historical footnote worth mentioning here. The term habitable zone didn't enter scientific vocabulary until relatively recently. Astronomer Su-Shu Huang introduced the concept in 1959, though the underlying idea that Earth's distance from the Sun enables life goes back much further. Researchers still argue about the most appropriate criteria for defining habitable zone boundaries, with some preferring conservative estimates based on geological analogies and others advocating for optimistic boundaries that account for more speculative scenarios. The planet in question falls within even the most conservative definitions, which strengthens confidence in its habitability. A quirky complication involves tidal locking, the phenomenon where a planet always shows the same face to its star, just as the moon always shows the same face to Earth. Planets orbiting close to their stars, as many habitable zone planets around K-type and M-type dwarfs must do, often become tidally locked over time. One hemisphere bakes in perpetual day while the other freezes in endless night. This arrangement might seem hostile to life, but climate models suggest that atmospheric circulation could redistribute heat effectively enough to maintain habitable conditions in certain regions, particularly along the boundary between day and night hemispheres. The planet we're discussing shows uncertain evidence regarding tidal locking. Its 30-hour rotation period suggests it has not fully locked to its star, but whether this represents a stable long-term state or a transitional phase remains unclear. Some models predict eventual locking over billions of years, while others suggest resonances or other factors could prevent complete synchronization. The question matters for habitability assessments, as tidal locking would fundamentally alter climate patterns and potentially constrain where life could thrive. The habitable zone concept also ignores subsurface environments where life might flourish regardless of surface conditions. Jupiter's moon Europa possesses a global ocean beneath its icy crust, heated by tidal forces rather than stellar radiation. Saturn's moon Enceladus shows similar evidence of liquid water underground. These moons orbit far outside the Sun's traditional habitable zone, yet might harbor conditions suitable for life. When assessing exoplanets, scientists must consider whether habitability extends beyond the planet's surface to potential underground or underwater environments. For the planet in question, however, the evidence points towards surface habitability, rather than merely subsurface possibilities. The atmospheric biosignatures detected by Webb imply biological activity occurring at or near the surface, where photosynthesis or equivalent processes could generate oxygen and methane. Subsurface life, if it existed on this world, would likely not produce the atmospheric signatures observed. The biosignatures suggest something happening in the open, under alien skies, where starlight drives chemistry and life cycles. You feel yourself sinking deeper into relaxation as these concepts blend together into a coherent picture. A planet orbiting at the right distance from a stable star, possessing an atmosphere with the right composition to maintain temperate conditions, showing chemical evidence of ongoing biological activity. Each piece of evidence reinforces the others, creating a case that grows stronger with every observation. The habitable zone framing helps communicate why this discovery matters to a public accustomed to hearing about exoplanet detections that ultimately disappoint. Most exoplanets found to date orbit too close or too far from their stars for liquid water, or lack atmospheres entirely, or show compositions incompatible with life as we understand it. This planet threads the needle, satisfying multiple criteria simultaneously in ways that demand attention. The question of what lies beneath those alien clouds, what surface might exist below the atmosphere Webb has analyzed, leads us into considerations of planetary mass and composition. You see, not every world with a favorable atmosphere would necessarily offer a place to stand. Gas giants like Jupiter and Saturn possess atmospheres aplenty, but no solid surface beneath them, just layers of increasingly dense gas transitioning eventually to metallic hydrogen under crushing pressures. For life as we know it, something solid or liquid beneath the sky seems necessary, or at least highly advantageous. The planet orbiting our K-type star falls into a category astronomers call super-Earths, worlds larger than our home planet but smaller than the ice giants Uranus and Neptune. With an estimated diameter about 1.4 times Earth's and a mass perhaps 3 to 4 times greater, this planet possesses enough gravity to retain a substantial atmosphere, but not so much that it would crush any surface structures under enormous pressure. The density calculations, derived from the combination of mass and radius estimates, suggest a rocky composition similar to Earth's, with an iron-nickel core surrounded by a silicate mantle and possibly a crust bearing familiar minerals. You might wonder how scientists determine the mass of a planet they can only observe indirectly through transit dimming. The answer involves that radial velocity technique mentioned earlier, where the gravitational tug of a planet causes its star to wobble slightly. The magnitude of this wobble reveals the planet's mass, while the transit observations reveal its radius. Dividing mass by volume yields density, and density constrains what materials could compose the planet's interior. A density similar to Earth's, around 5 grams per cubic centimeter, strongly suggests rocky composition. A much lower density would indicate gas or ice, while higher density might imply an iron-heavy world. The super-Earth category encompasses an enormous range of possibilities, some of which remain purely hypothetical. Ocean worlds entirely covered in water kilometers deep, their rocky cores never touching atmosphere. Lava planets with surfaces molten from tidal heating or proximity to their stars. Diamond planets where carbon-rich interiors crystallize under pressure into planet-sized gemstones. The specific characteristics depend on formation history, orbital evolution, and countless factors that each planetary system handles differently. Historians of planetary science note that the super-Earth concept barely existed before the exoplanet era, as our own solar system lacks any examples in this size range. For the planet under consideration, the evidence tilts towards something resembling a scaled-up Earth rather than an exotic configuration. The atmospheric composition suggests ongoing geological activity, with volcanic processes potentially contributing carbon dioxide and water vapor, even as biological processes dominate the oxygen and methane budgets. Active geology requires internal heat, which in turn implies a metallic core capable of generating a magnetic field through dynamo action. This planetary magnetism brings us to our next topic, but let's first appreciate the picture emerging from mass and density considerations. A rocky world with continents and oceans seems increasingly plausible as we accumulate evidence. The surface gravity, roughly 1.3 to 1.5 times Earth's, would feel noticeable to a human visitor, but not debilitating. You'd weigh more, tire faster climbing stairs, but basic locomotion would remain possible. Of course, no human will visit this world anytime soon given the distances involved, but imagining the physical experience helps make the planet feel real rather than abstract. There's a quirky aspect to super-Earth formation that planetary scientists continue debating. In our solar system, no planet occupies the size range between Earth and Neptune, leaving a gap that seemed unremarkable until exoplanet surveys revealed that super-Earths and mini-Neptunes are actually the most common type of planet in the galaxy. Why did our solar system skip this category? Some theories invoke Jupiter's early migration, disrupting the formation of intermediate-sized planets. Others suggest our solar system simply represents an unusual outcome in the cosmic lottery. Researchers still argue about which explanation best fits the evidence. The question of whether super-Earths can support plate tectonics, that restless shuffling of continental plates that shapes Earth's surface and regulates our climate, remains contentious. Some models suggest that higher gravity and thicker lithospheres might suppress plate motion, leaving super-Earths with stagnant lid tectonics, where heat escapes primarily through volcanic hotspots, rather than spreading ridges and subduction zones. Other models predict that larger mantles generate more heat, driving even more vigorous tectonics than Earth experiences. The answer matters because plate tectonics influences everything from atmospheric composition to the long-term stability of surface conditions. For habitability assessments, the key question is whether the planet can maintain the cycles that life seems to require. Water cycling between atmosphere and surface, carbon cycling between rocks and air, nutrients cycling through ecosystems. These cycles depend on geological activity, and geological activity depends on planetary interior properties that we can only infer indirectly from mass and radius measurements. The inference for this planet suggests an active interior capable of supporting the necessary cycling, but considerable uncertainty remains. You feel the solid ground of evidence building beneath these speculations, even as gaps and questions persist. A world takes shape in your imagination. Rocky underfoot, atmosphere overhead, water somewhere in between. Not a gas giant's endless depths, nor an ice world's frozen silence, but something recognizably planetary in the terrestrial sense. Something that might, just might, harbor surfaces where biology has done interesting things over billions of years. The next piece of the puzzle concerns protection from the harsh realities of space, the magnetic shield that guards Earth from solar radiation and cosmic rays. Without such protection, even the most promising atmospheric chemistry might prove irrelevant, stripped away by stellar winds or rendered hostile by ionizing radiation. Magnetic fields don't get the attention they deserve in popular discussions of planetary habitability, but they function as invisible guardians that make complex life possible on worlds like Earth. Our planet generates its magnetic field through the dynamo action of its liquid iron outer core, where convection currents in electrically conductive metal produce electric currents that in turn generate magnetic fields. This field extends far into space, creating a protective bubble called the magnetosphere that deflects the worst of the solar wind and cosmic radiation away from our atmosphere and surface. Without Earth's magnetic field, the consequences would be severe. The solar wind, that constant stream of charged particles flowing from the sun, would directly interact with our upper atmosphere, gradually stripping away lighter gases and potentially eroding the atmosphere entirely over geological timescales. Mars may have lost its once thicker atmosphere partly because it lacks a global magnetic field, leaving its surface exposed to solar wind erosion. Venus, despite lacking a significant magnetic field, retains a thick atmosphere because its close proximity to the sun creates ionospheric processes that provide some protection. But Venus's surface conditions demonstrate that atmospheric retention alone doesn't guarantee habitability. For the exoplanet we're examining tonight, evidence of a magnetic field comes indirectly and tentatively. The presence of a substantial atmosphere over billions of years suggests that something protects it from stellar wind stripping. The K-type host star, while calmer than many red dwarfs, still produces stellar winds and occasional flares that would erode an unprotected atmosphere. The fact that the atmosphere persists, showing biosignatures that imply long-term stability, supports the inference that magnetic shielding exists. More direct evidence might come from detecting auroral emissions or radio waves associated with magnetic interactions between the planet and stellar wind. But current instruments lack the sensitivity to detect such signals from exoplanets at this distance. Future generations of telescopes and radio arrays might achieve such detections, providing more definitive answers about exoplanetary magnetism. For now, scientists rely on theoretical modeling and indirect inference. The model suggests that a planet of this mass and composition could indeed generate a magnetic field through core dynamo action, assuming its interior remains hot enough to maintain liquid metal convection. A planet 3 to 4 times Earth's mass would possess a larger core under higher pressure, potentially altering dynamo dynamics in ways that remain poorly understood. Some models predict stronger fields than Earth's, while others suggest the increased pressure might suppress convection and weaken the dynamo. Researchers continue arguing about how magnetic field strength scales with planetary mass. There's a quirky historical episode worth recounting here. In the early 20th century, some scientists believed Earth's magnetic field originated from the planet's rotation, a theory that seemed reasonable until physicists demonstrated that rotation alone couldn't explain observed magnetic properties. The dynamo theory that replaced it took decades to develop and still contains uncertainties that modern supercomputers struggle to resolve. Simulating planetary dynamos requires capturing physical processes across scales from millimeters to thousands of kilometers, a computational challenge that pushes the limits of current technology. For habitability on the surface of our target planet, a magnetic field matters not just for atmospheric retention, but for protecting any living organisms from ionizing radiation. Earth's magnetosphere shields surface life from most cosmic rays and solar energetic particles, which would otherwise damage DNA and other biological molecules. Deep underground or underwater, life could potentially survive without this protection, but surface and atmospheric life would face significant challenges on an unshielded world. The detection of biosignatures implying surface-level biological activity strengthens the case for magnetic protection. Photosynthesis, the most likely source of atmospheric oxygen, requires organisms living at or near the surface where starlight penetrates. If radiation levels were too high for surface life, the oxygen-methane disequilibrium might not exist or would require different explanations. The biosignatures themselves thus serve as indirect evidence that the planetary surface offers protection compatible with biology. You feel comforted by the thought of an invisible shield guarding this distant world. Just as Earth's magnetic field guards our own biosphere, the universe contains many hazards, from stellar flares to cosmic ray bursts, and life requires shelter from these dangers to persist over the billions of years needed for evolution to produce complexity. A magnetic field represents one such shelter, a planetary defense system generated by the simple physics of convection and conductivity. The planet grows more Earth-like in your imagination with each revelation: rocky surface, temperate climate, protective magnetism. The differences remain significant, of course. Higher gravity, different atmospheric proportions, an orange sun instead of yellow, and a year lasting 42 Earth days instead of 365. But the similarities outweigh the differences in ways that suggest the basic template for life-bearing worlds might be more universal than some skeptics have argued. As we continue our exploration, we'll examine the statistical framework that produced that remarkable 99.7% probability, understanding exactly what this number means and what limitations it carries. But first, let another breath settle your thoughts. The universe has provided a candidate world for extraterrestrial life, complete with atmospheric chemistry that screams biology and physical conditions that whisper hospitality. The evidence accumulates, the picture clarifies, and the implications spread outward like ripples in a cosmic pond. The night deepens around you, but the light from a distant star carries news that challenges everything humanity has assumed about its place in the cosmos. The 99.7% figure that headlines trumpeted and skeptics questioned emerges from a statistical framework called Bayesian inference, a method of reasoning that might sound intimidating but actually reflects how rational minds naturally update beliefs in light of new evidence. As you settle deeper into your evening rest, let's walk through what this number means, how scientists calculated it, and what caveats accompany any such probability estimate. Bayesian reasoning begins with a prior probability, your initial estimate of how likely something is before considering new evidence. For the existence of life on any given exoplanet, astronomers might start with a very low prior, perhaps 1 in a million or even less, reflecting the vast number of planets that appear lifeless compared to the single example of life we know. This prior captures our uncertainty and the base rate of life in the universe, as far as we understand it. Evidence then updates this prior through a mathematical relationship that accounts for how likely the observed evidence would be if life existed versus if it didn't. If life on a planet makes certain observations much more probable than life's absence would, the evidence strongly supports the life hypothesis, shifting the calculated probability upward. If the evidence could equally well be explained with or without life, it barely moves the needle. The strength of evidence lies in its ability to discriminate between competing hypotheses. For the planet we're discussing, the evidence consists of multiple atmospheric detections: oxygen, methane, water vapor, nitrogen, and their specific concentrations and combinations. The researchers constructed what they call a Bayesian biosignature framework, assigning likelihoods to each observation under both biological and non-biological scenarios. The oxygen-methane disequilibrium, as we discussed, appears far more likely if life exists than if it doesn't, since known abiotic processes struggle to maintain such imbalance. The water vapor and temperate conditions boost the probability further by confirming habitability. Each piece of evidence contributes multiplicatively to the final calculation. The result, after incorporating all available data and reasonable assumptions about priors and likelihoods, landed at that striking 99.7%. In scientific terms, this represents a posterior probability, the updated belief after all evidence has been considered. It does not mean life definitely exists, only that given everything we observe, the hypothesis that life exists appears vastly more probable than the hypothesis that it doesn't. There's a crucial subtlety here that deserves attention. The prior probability matters enormously in Bayesian calculations. If you start with an extremely low prior, even strong evidence might not push the posterior very high. The researchers who conducted this analysis used priors informed by our understanding of planetary formation, chemistry, and the conditions necessary for life, priors that some critics argue may be too optimistic. Scholars still debate exactly how to set priors for life detection, given our sample size of exactly one inhabited planet. Different prior assumptions could yield different posterior probabilities from the same data. A quirky aspect of Bayesian reasoning is that two rational observers with different priors could examine identical evidence and reach different conclusions, both validly within the framework. This isn't a bug but a feature, honestly acknowledging that prior beliefs influence how we interpret new information. The 99.7% figure thus represents not absolute truth, but the conclusion reached by researchers using specific assumptions that they justify in their papers and defend against challenges. The framework also incorporates uncertainty about the likelihood assignments themselves. How probable is it that abiotic processes could produce the observed oxygen levels? Scientists don't know precisely, so they estimate ranges and propagate this uncertainty through their calculations. The final probability carries error bars, though headlines rarely report them. A more complete statement might be that the probability of life falls between 97 and 99.9% at a 95% confidence level, or some similar interval that conveys the inherent uncertainty. The comparison to other claimed biosignature detections provides useful context. When phosphine was tentatively detected in Venus's atmosphere in 2020, initial estimates of biological probability ran much lower, perhaps tens of percent rather than 90+, because alternative explanations seemed more plausible, and the detection itself faced questions. Subsequent analyses have cast further doubt on the Venus phosphine claim, illustrating how initial excitement can fade as scrutiny intensifies. The planet we're discussing tonight has weathered more scrutiny than Venus phosphine while maintaining higher probability estimates, which strengthens confidence in the finding. You might reasonably ask what it would take to push the probability higher still. Approaching certainty, scientists generally agree that direct detection of biological molecules more complex than simple gases, perhaps specific biomarkers unique to living systems or resolved images of surface features consistent with biology, would clinch the case. Alternatively, detection of radio signals or other technosignatures indicating intelligent life would remove all doubt. Short of such dramatic evidence, we're left with probability estimates that, however high, retain some residual uncertainty. The 99.7% figure represents the strongest case for extraterrestrial life ever made based on empirical evidence. Previous candidates have failed to achieve comparable confidence levels. This doesn't guarantee the finding will survive future scrutiny, but it establishes a high watermark in the long history of searching for life beyond Earth. You let the numbers settle into intuition, transforming statistics into feeling. Almost certainly, something lives on that world. Almost certainly, we are not alone. The remaining uncertainty provides space for humility and continued inquiry. But the dominant probability now favors companionship over isolation in the cosmic silence. Not everyone in the scientific community has greeted these findings with champagne and celebration. Skeptics, that essential element of healthy scientific discourse, have raised objections that deserve serious consideration. As you continue your drift towards sleep, let's examine the counter-arguments, because understanding why some experts remain cautious will deepen your appreciation of both the evidence and its limitations. The most persistent objection concerns the possibility of abiotic processes that current models simply haven't considered. Chemistry, after all, operates according to universal laws. But those laws can produce surprising outcomes under conditions we haven't explored. Exotic photochemistry driven by the specific spectrum of the K-type host star, volcanic processes involving mineral combinations not found on Earth, reactions catalyzed by cosmic ray bombardment in the upper atmosphere. Each represents a potential alternative explanation that skeptics urge should be investigated before jumping to biological conclusions. One prominent critic, a geochemist who has spent decades studying planetary atmospheres, argues that the oxygen detection might result from runaway water loss during the planet's early history. If the young planet experienced a moist greenhouse phase where water vapor dominated the upper atmosphere, intense ultraviolet radiation could have dissociated water molecules faster than hydrogen could escape, leaving behind oxygen that accumulated over billions of years. This mechanism, sometimes called abiotic oxygen buildup, has been proposed for other potentially habitable worlds and cannot be easily ruled out from spectral data alone. The methane detection faces similar scrutiny. While methane and oxygen together create the disequilibrium that points toward biology, some researchers note that geological processes might produce methane in ways not adequately captured by current models. Serpentinization, the reaction between water and certain iron-rich minerals, produces methane without any biological involvement and occurs in Earth's ocean floors. If the planet has widespread volcanic activity and water-rock interactions, serpentinization could contribute methane at rates sufficient to maintain atmospheric concentrations alongside whatever oxygen sources exist. There's a historical parallel worth remembering here. When astronomers first detected methane in Mars's atmosphere using Earth-based telescopes in 2004, excitement rippled through the scientific community. Methane on Mars could indicate either geological activity or, tantalizingly, biological methanogenesis beneath the surface. 2 decades later, the Martian methane mystery remains unresolved, with observations yielding inconsistent results and no consensus on whether the methane is real, how much exists, or what produces it. Researchers still argue about interpretation of Martian atmospheric data, a reminder that initial detections often prove more complicated than they first appear. Instrument calibration and systematic errors represent another category of concern. Webb's instruments operate at the very edge of their designed capabilities when extracting atmospheric signatures from transit observations. Tiny systematic effects, if uncorrected, could mimic molecular absorptions or distort abundance estimates. The research team has run extensive checks and validated their calibration against known standards, but skeptics argue that truly novel systematic errors might evade such checks, producing false positives that only become apparent through future observations. A quirky objection comes from a small but vocal group of researchers who question the theoretical frameworks underlying biosignature interpretation itself. They argue that our understanding of atmospheric chemistry derives almost entirely from solar system examples, a sample too limited to capture the full range of planetary behavior. Perhaps atmospheres operate differently around K-type stars, or planets in this mass range follow evolutionary paths we haven't imagined. Without better theoretical grounding, they suggest, assigning high probabilities to biological explanations may be premature. The scientific community handles such objections through ongoing observation, analysis, and debate. No single paper settles major questions. Instead, understanding accumulates gradually as multiple independent teams examine the same data, propose alternative models, and test predictions against new observations. The planet in question will receive continued scrutiny for years or decades, with each additional observation either strengthening the biological hypothesis or revealing complications that shift probability estimates downward. You might find some comfort in this skeptical process rather than discouragement. Science works precisely because it demands evidence withstand challenge before achieving acceptance. The 99.7% probability reflects findings that have already survived considerable scrutiny, more than most claimed biosignatures ever face. The skeptics who continue questioning the interpretation perform a valuable service, preventing premature conclusions and ensuring that when scientific consensus eventually emerges, it will rest on solid foundations. The debate continues in journals, conferences, and late-night conversations among researchers who disagree about specifics while sharing commitment to understanding. Some will change their minds as evidence accumulates, others will maintain skepticism until more definitive data arrives. This is science functioning as intended, messy and contentious in real time, but ultimately converging toward truth through relentless testing of ideas against reality. For tonight, you can hold both possibilities in mind: the strong probability that life exists on this distant world, and the residual uncertainty that keeps scientists humble. The universe doesn't owe us easy answers, but it has provided evidence far stronger than anything previous generations could have imagined. Whether that evidence eventually proves conclusive or leads to revisions and reinterpretations, the journey of discovery continues. Before we invest too heavily in excitement about this particular planet, history offers sobering lessons about premature announcements of extraterrestrial life. The scientific literature contains a graveyard of claimed detections that ultimately failed to survive scrutiny, each teaching valuable lessons about the difficulty of distinguishing genuine biosignatures from abiotic mimics. As your mind wanders toward sleep, let's revisit some of these historical false alarms and consider what they teach us about the current findings. The most notorious recent episode involves the claimed detection of phosphine in Venus's atmosphere, announced with great fanfare in September 2020. Phosphine, a molecule consisting of one phosphorus atom bonded to 3 hydrogens, appeared in spectral data from ground-based telescopes at concentrations that known abiotic chemistry couldn't explain. The researchers who announced the finding explicitly raised the biological possibility, noting that on Earth, phosphine is produced primarily by anaerobic microorganisms. Headlines blared about potential life in Venus's clouds, a notion that seemed outlandish given Venus's hellish surface temperatures, but perhaps plausible in cooler atmospheric layers. Within months, the phosphine claim began unraveling. Reanalysis of the same data by independent teams suggested the detection might be spurious, an artifact of data processing rather than genuine molecular absorption. Other researchers pointed to potential contamination from sulfur dioxide, a molecule with spectral features that can mimic phosphine under certain conditions. Subsequent observations by different instruments failed to confirm the original detection, and the original team eventually acknowledged significant uncertainties in their initial analysis. The Venus phosphine saga illustrates how quickly scientific enthusiasm can outpace the careful work needed to confirm extraordinary claims. Mars has provided its own lessons in humility. Beyond the methane controversy mentioned earlier, the most dramatic false alarm came in 1996, when NASA scientists announced that a meteorite from Mars, designated ALH84001, contained microscopic structures resembling fossilized bacteria. President Clinton addressed the nation about the finding, and public excitement soared. However, subsequent research demonstrated that the structures could form through non-biological processes, and the scientific consensus shifted away from the biological interpretation. The Martian meteorite remains a fascinating object of study, but not as evidence of extraterrestrial life. There's a quirky episode from the 19th century that deserves mention. When spectroscopy was first applied to astronomy, some researchers claimed to have detected signatures of vegetation on Mars, supposedly explaining the planet's seasonal color changes. These claims persisted for decades before improved observations revealed that the color variations resulted from dust storms rather than growing plants. The embarrassment taught astronomers to be cautious about interpreting ambiguous data through biological lenses. What distinguishes the current exoplanet findings from these historical episodes? Several factors suggest greater robustness. First, the detection involves multiple biosignatures rather than a single ambiguous signal. Oxygen, methane, water vapor, and favorable physical conditions together create a more compelling case than anyone would alone. Second, the observations come from Webb, an instrument specifically designed for this type of measurement, rather than repurposed equipment at the edge of its capabilities. Third, the data has survived peer review and multiple rounds of independent reanalysis, more vetting than most initial claims receive. But caution remains appropriate. The 99.7% figure, while high, explicitly acknowledges a 0.3% possibility that something other than biology explains the observations. Future observations might reveal complications that shift this probability downward. The history of claimed biosignatures teaches that initial confidence often proves excessive, that nature excels at mimicking biology through abiotic processes in ways that only become apparent after extensive investigation. The research team themselves emphasized the preliminary nature of their conclusions, calling for additional observations and welcoming skeptical analysis. This humility represents good scientific practice, acknowledging uncertainty while presenting evidence as straightforwardly as possible. The 99.7% figure isn't a claim of certainty, but a probabilistic assessment subject to revision as knowledge advances. You might feel the weight of these historical lessons pressing against the excitement that the current findings inspire. That tension is appropriate and healthy. Science advances through a dialectic between enthusiasm and skepticism, with genuine discoveries surviving challenges that expose false positives. The planet orbiting that distant K-type star currently holds the strongest candidacy for extraterrestrial life ever established. But strongest ever doesn't mean certain, and future observations will ultimately determine whether this candidate joins the graveyard of false alarms or stands as the breakthrough that changes everything. For tonight, hold both possibilities lightly. The evidence is real and the probability calculations are rigorous, but history counsels patience. If life truly exists on that distant world, it will still be there next year and next decade, providing opportunities for confirmation that remove all doubt. If alternative explanations emerge, science will revise its conclusions accordingly. Either outcome represents progress in understanding our place in the universe. The investigation continues, and you're witnessing it unfold in something close to real time, a privilege that previous generations could only dream of. If life does exist on this distant world, what might it look like? The question invites speculation that ranges from conservative extrapolation of Earth biology to wild imagination of entirely alien biochemistries. As you drift deeper into your pre-sleep reverie, let's explore the possibilities, acknowledging up front that any answer involves more guesswork than certainty. The beauty of this moment in scientific history lies precisely in the uncertainty, the open canvas upon which imagination and evidence collaborate to paint pictures of alien existence. The most conservative hypothesis suggests life resembling Earth's in fundamental ways: carbon-based biochemistry using water as a solvent, storing genetic information in nucleic acids, building structures from proteins and lipids. This conservatism isn't mere failure of imagination, but reflects the apparent ubiquity of the chemical building blocks involved. Carbon atoms are uniquely capable of forming complex, stable molecules at temperate conditions. Water's properties make it an ideal medium for biochemistry. Amino acids, the building blocks of proteins, form spontaneously in laboratory simulations of prebiotic chemistry and have been found in meteorites scattered throughout our solar system. Perhaps these same ingredients combine on other worlds to produce life fundamentally similar to Earth's at the molecular level. following a universal recipe written in the laws of chemistry themselves. Under this scenario, the planet's oxygen-methane atmosphere might indicate photosynthetic organisms capturing stellar energy and releasing oxygen, while methanogenic organisms in anaerobic niches produce methane. The analogy to Earth's biosphere would be strong. Primary producers harnessing light energy, decomposers recycling nutrients, perhaps even complex multicellular organisms, if evolution has had sufficient time to work its incremental magic. 6 billion years of planetary history provides ample time for complexity to emerge, given that Earth's biosphere produced complex multicellular life within 4 billion years. The extra 2 billion years this planet has enjoyed could have allowed evolution to explore possibilities Earth hasn't yet reached. Imagine microbial mats coating rocks along alien shorelines, their pigments tuned to absorb the slightly redder light of the K-type star. These photosynthetic communities would appear different colors than Earth's vegetation, perhaps deep red or purple rather than green, optimized for different stellar spectra. The chlorophyll that Earth plants use absorbs red and blue light while reflecting green, but alien pigments might follow different strategies, absorbing the wavelengths most abundant in their star's output. A forest on this world might look like autumn year-round to human eyes, painted in oranges and crimsons that we associate with dying leaves, but they signify vibrant growth. A more speculative possibility involves life using different chemical foundations than Earth's. Silicon sometimes appears in science fiction as an alternative to carbon, since silicon shares carbon's ability to form 4 bonds and thus could theoretically build complex molecules. However, silicon-based biochemistry faces significant challenges that make it seem unlikely in most environments. Silicon compounds tend to be less stable and less soluble than their carbon counterparts, and silicon lacks the versatility carbon displays in forming double and triple bonds essential for biological information storage. Most astrobiologists consider silicon-based life less likely than carbon-based, but not impossible under exotic conditions, far removed from what this particular planet seems to offer. There's a quirky historical footnote here worth sharing as your mind wanders towards sleep. In the early 20th century, before biochemistry was well understood, some scientists speculated that life on other worlds might use entirely different solvents than water. Ammonia, methane, hydrogen fluoride, and even stranger substances were proposed as alternatives around which alien biochemistry might organize itself. While these possibilities haven't been entirely ruled out, improved understanding of chemistry has made them seem less plausible for producing the complex, self-reproducing systems we call life. Researchers still debate whether non-aqueous biochemistry could ever achieve the complexity necessary for evolution and adaptation, but the consensus leans toward water as nearly irreplaceable. The atmospheric biosignatures detected on the exoplanet don't directly reveal what organisms produce them, only that some ongoing process maintains chemical disequilibrium. The oxygen could come from photosynthesis, performed by organisms ranging from microscopic algae-like cells to vast forests of alien plants, or from some biological process entirely unlike anything on Earth. The methane might derive from methanogenic microbes thriving in oxygen-poor environments, from digestive processes of larger organisms similar to Earth's cattle and termites, or from metabolisms we haven't imagined operating under conditions we don't fully understand. The data constrains possibilities but doesn't select definitively among them. What about intelligent life? The detection of biosignatures suggests a biosphere, but biospheres don't necessarily produce technological civilizations. Earth has harbored life for nearly 4 billion years, but technological humans for perhaps a few 100,000, a ratio that suggests intelligence is a rare outcome of evolution, rather than an inevitable endpoint. The planet might host only microbial life, simple and abundant, but lacking the complexity we associate with animals and plants. Or it might support complex ecosystems without any species approaching tool use and abstract thought. Or perhaps civilizations rose and fell there before Webb ever looked their way, leaving no traces detectable across light years of space. Some researchers have proposed searching for technosignatures alongside biosignatures, looking for radio emissions, artificial lighting on the night side, or atmospheric pollutants that would indicate industrial activity. The current observations don't reveal any such signals, but absence of evidence isn't evidence of absence, especially given the immense challenges of detecting technosignatures at interstellar distances. A civilization at our technological level, broadcasting radio waves into space, would produce signals far too weak to detect from this distance with current instruments. The search for extraterrestrial intelligence continues scanning the skies for signals that would resolve the question more definitively than atmospheric chemistry ever could, but so far, the cosmic silence persists. You might imagine walking on the surface of this world if imagination permits such extravagance during your drowsy contemplation. The gravity would feel strange, your steps heavier than on Earth but manageable with adjustment. The sky might glow with unfamiliar colors at dawn and dusk, the K-type star's orange light scattering through an atmosphere slightly different from our own. Clouds of water vapor would drift overhead, perhaps shaped by winds following patterns no Earth meteorologist could predict. If oceans exist, waves would lap against shores of unknown minerals, their rhythms set by moons we haven't detected or tidal forces we can only model. The life there, whatever its form, would have evolved under these specific conditions for billions of years. Every organism would be exquisitely adapted to its environment, shaped by selection pressures we can only guess at. Predators and prey, if such categories apply, would have developed strategies and counter-strategies through countless generations. Ecosystems would cycle energy and nutrients through webs of interaction as complex as any on Earth, perhaps more complex given the additional time available. The sheer creativity of evolution, given a planet of possibilities and eons of time, defies prediction. Historians of science often note that discoveries about life on Earth have consistently revealed greater diversity and resilience than anyone anticipated. Extremophiles thriving in boiling hot springs, freezing Antarctic lakes, crushing deep-sea pressures, and acidic volcanic pools expanded our conception of habitable environments dramatically. Each discovery suggests that life, once started, finds ways to persist and diversify under conditions that seem hostile by human standards. This pattern of surprise should inform our expectations about alien life, preparing us for organisms stranger than current imagination can conjure. For now, the planet keeps its secrets, revealing only the atmospheric chemistry that hints at biological activity beneath. What walks or swims or floats through that alien biosphere remains unknown, a mystery that future observations and perhaps future missions might eventually illuminate. The night grows deeper around you, and the question of alien forms dissolves into the comfortable uncertainty of dreams about to begin. The possibility that intelligent beings might inhabit this distant world opens questions that extend beyond biology into philosophy, sociology, and the very nature of communication across cosmic distances. As you settle further into the comfortable embrace of your bed, let's explore what it might mean if the life on this planet has evolved not just complexity, but consciousness, not just adaptation, but awareness. The search for extraterrestrial intelligence, known by its acronym SETI, has pursued this question for decades, and the discovery of a high-probability biosignature world adds new urgency to their efforts. SETI began in earnest in 1960 when astronomer Frank Drake pointed a radio telescope at two nearby stars and listened for artificial signals. He heard nothing beyond natural cosmic noise, but the experiment established a methodology that has continued and expanded ever since. Radio telescopes around the world have scanned millions of stars across billions of frequencies, searching for patterns that could not arise from natural processes. The iconic Arecibo message, transmitted in 1974 toward a globular cluster, represented humanity's first deliberate attempt to announce our presence to potential listeners. The message encoded basic information about our chemistry, our solar system, and our forms, using a simple binary code that any mathematically sophisticated civilization should be able to decode. The discovery of a planet with strong biosignature evidence immediately prompted SETI researchers to add it to their target lists. If life exists there, perhaps intelligent life exists too. And perhaps that intelligent life has developed technology capable of producing detectable signals. Radio telescopes have already begun monitoring the star system for artificial transmissions, though no signals have been detected yet. The absence of signals doesn't discourage searchers, who note that our own radio leakage would be nearly undetectable from that distance with current technology. A civilization would need to deliberately beam powerful, focused transmissions toward our solar system for us to have any chance of detecting them. There's a fascinating philosophical puzzle embedded in SETI's methodology called the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" during a lunch conversation in 1950. Given the age and size of our galaxy, if intelligent life arises with any reasonable frequency, civilizations should have had time to spread across the stars, or at least make their presence known through detectable signals. Yet we observe no obvious evidence of galactic civilization, no megastructures blocking starlight, no radio beacons announcing alien presence. The paradox admits many possible resolutions, from the grim possibility that civilizations tend to destroy themselves before achieving interstellar presence, to the more hopeful notion that we simply haven't looked hard enough or in the right ways. The planet we've been discussing tonight intersects with the Fermi paradox in interesting ways. If life evolved there 6 billion years ago, any intelligent species arising from that biosphere would have had a billion-year head start on humanity. A billion years represents an almost incomprehensible span for technological development, enough time to colonize the entire galaxy multiple times over if the will and capability existed. The fact that we see no evidence of such colonization from this or any other system might suggest that intelligence remains rare even where life flourishes, or that technological civilizations choose not to expand aggressively, or that our detection methods miss whatever signals they produce. Researchers still argue about the most productive strategies for SETI, with some favoring continuous monitoring of promising targets and others advocating for all-sky surveys that might catch transient signals from unexpected directions. The discovery of a high-probability life-bearing world provides a compelling target for focused observation, but the vastness of possibility space means that even targeted efforts might miss signals if they occur outside the monitored frequency bands or time windows. The search continues with patience born of necessity, as the alternative to patient searching is abandoning the quest entirely. A quirky aspect of SETI involves the question of what we would do if a signal were actually detected. International protocols exist governing the verification and announcement of any confirmed extraterrestrial signal, designed to prevent premature claims and ensure that such momentous news reaches humanity through proper channels. The SETI community has debated extensively whether and how to respond to any detected signal, with opinions ranging from immediate enthusiastic reply to cautious silence until the implications can be fully assessed. The discovery of a likely inhabited world adds new dimensions to these discussions, as any detected signal would now come with context about the biological nature of its senders. The implications of contact with extraterrestrial intelligence extend far beyond science into every domain of human thought and culture. Religions would face profound challenges to cosmologies built around Earth's special status, though many theologians have already begun incorporating the possibility of extraterrestrial life into their frameworks. Political structures might shift as humanity confronts an external perspective on our internal divisions. Economic systems could transform if contact brought new knowledge or technologies, or could destabilize if fear and uncertainty dominated public response. Philosophers would grapple with questions of consciousness, morality, and meaning that suddenly acquire practical dimensions rather than remaining purely abstract. You might wonder whether beings on that distant world have detected us, whether their telescopes have analyzed Earth's atmosphere and found the same biosignatures we've found on theirs. The light currently reaching them from our solar system left Earth years ago, carrying spectral information about our atmosphere's composition. If their technology matches or exceeds ours, they could in principle detect Earth's oxygen, methane, water vapor, and even the artificial chemicals we've added to our atmosphere through industrial activity. The notion of mutual discovery, two civilizations simultaneously realizing they're not alone, carries a romantic appeal that science fiction has explored extensively, but that might actually be occurring right now across the light years separating us. Communication, if it ever becomes possible, would face challenges beyond mere distance. The speed of light imposes a delay that makes conversation impossible in any human sense. Messages would take years to travel each way, turning dialogue into exchange of monologues. Language presents an even more fundamental barrier, as any alien communication system would presumably bear no resemblance to human languages, requiring decipherment efforts that might take generations. Yet mathematics and physics operate identically throughout the universe, providing a potential common ground for initial contact. Prime numbers, fundamental constants, and basic physical relationships could serve as starting points for demonstrating intelligence and building shared vocabulary. The night deepens around you as these speculations swirl through your drowsy mind. Somewhere out there, perhaps, beings are looking back at our star and wondering the same things we wonder about them. The cosmic silence might mask countless conversations we simply cannot hear yet, or might reflect genuine loneliness that makes every glimmer of possible companionship precious beyond measure. Either way, the discovery of a high-probability biosignature world brings these questions from the realm of pure speculation into the domain of targeted investigation, focusing human curiosity on a specific point of light in the endless dark. The excitement surrounding this discovery has already catalyzed planning for future missions and instruments designed to learn more about this tantalizing world. Science never rests content with current knowledge when mysteries remain unsolved, and the mystery of whether life truly exists on this distant planet demands resolution that only better observations can provide. As you relax into the gentle rhythm of approaching sleep, let's explore what comes next in humanity's quest to answer the question that has haunted us since we first looked up at the stars. The James Webb Space Telescope will continue observing this planet, accumulating more transits and refining the atmospheric measurements that produce the current biosignature detections. Each additional observation improves the signal-to-noise ratio, potentially revealing fainter spectral features that could strengthen or complicate the biological interpretation. Scientists have proposed dedicated observing programs that would monitor the planet continuously during multiple orbital periods, searching for variations in atmospheric composition that might indicate seasonal cycles or other temporal patterns. Such variations would provide additional evidence for active biological processes, as living systems often display rhythms tied to environmental changes. Beyond Webb, the next generation of space telescopes already in planning stages could provide dramatically improved capabilities for exoplanet characterization. The Habitable Worlds Observatory, a proposed NASA flagship mission, would carry instruments specifically designed to directly image Earth-like planets around nearby stars and analyze their atmospheres with unprecedented precision. Direct imaging, as opposed to the transit method Webb employs, would allow observation of planets at any orbital phase rather than only during the brief windows when they pass in front of their stars. This capability would expand the number of observable planets enormously and enable detailed characterization that transit spectroscopy cannot achieve. The European Space Agency has proposed similar missions, including the Large Interferometer for Exoplanets, that would combine light from multiple spacecraft to achieve the angular resolution needed to see planets as distinct points separate from their host stars. Interferometry in space represents a tremendous technical challenge, requiring spacecraft to maintain positions relative to each other with nanometer precision while collecting light over baselines of hundreds of meters. If achieved, such instruments could potentially map surface features on nearby exoplanets, revealing continents, oceans, and perhaps even the glow of biological activity on nightside surfaces. Ground-based observatories contribute to the effort as well. The extremely large telescope under construction in Chile will feature a primary mirror 39 meters across, dwarfing any existing optical telescope and providing light-collecting power sufficient to detect atmospheric signatures on planets orbiting relatively nearby stars. Other extremely large telescopes planned for construction in Hawaii and elsewhere will add complementary capabilities. Together, these facilities will create a global network of planet hunting power that makes current instruments look primitive by comparison. There's a quirky historical pattern worth noting here. Major astronomical discoveries often come not from instruments designed to make them, but from new technologies applied in unexpected ways. Pulsars were discovered accidentally during radio surveys intended for other purposes. The cosmic microwave background was detected by engineers troubleshooting antenna noise. Even exoplanets themselves were first found using techniques developed for stellar astronomy rather than planetary science. Researchers still debate whether targeted searches or serendipitous discoveries drive astronomical progress more effectively, with most acknowledging that both play essential roles. The planet we've been discussing might eventually become a target for interstellar probes, though such missions remain beyond current technological capability. The Breakthrough Starshot initiative, funded by private philanthropy, aims to develop tiny spacecraft propelled by powerful ground-based lasers to velocities approaching 20% of light speed. At such speeds, a probe could reach the nearest stars within decades rather than millennia, returning images and data that would revolutionize our understanding of other planetary systems. The technical challenges are immense, from surviving the intense acceleration of laser propulsion to communicating results back across interstellar distances. But the initiative demonstrates that serious people are thinking seriously about interstellar exploration. For the biosignature world specifically, any probe mission would require travel times measured in decades or centuries, depending on propulsion technology. The scientists who launch such a mission would not live to see its results. The mission would become a gift to future generations, a message in a bottle tossed into the cosmic ocean by ancestors who believed the answers mattered, even if they couldn't witness them personally. This multi-generational aspect of deep space exploration challenges human institutions accustomed to planning on timescales of years, or at most decades, demanding new forms of organization capable of maintaining commitment across generations. In the nearer term, continued monitoring of the planet's host star might reveal additional planets in the system, some perhaps even better candidates for detailed study. Multi-planet systems are common in the galaxy, and the detection methods that found this world would likely have revealed any Jupiter-sized companions already. Smaller planets could remain hidden, awaiting observations with improved precision to tease out their signals from the noise. A system containing multiple potentially habitable worlds would provide comparative opportunities that single-planet systems cannot, allowing scientists to test hypotheses about what makes one planet develop life while another remains barren. The search for radio signals from the planet continues in parallel with atmospheric studies, SETI telescopes monitoring the star system for any hint of technological activity. Even a negative result carries information, constraining the probability that intelligent life has developed and chosen to broadcast its presence. The combination of biosignature detection and CD observation creates a more complete picture than either approach alone, probing both the existence of life and its potential advancement to technology producing intelligence. You feel the weight of these future efforts pressing gently against your consciousness, a reminder that the story we've traced tonight represents not an ending, but a beginning. The discovery of a high-probability biosignature world opens doors that will take decades or centuries to fully explore, launching research programs that will outlive everyone currently alive. Your moment of awareness, drifting towards sleep with visions of alien atmospheres floating through your mind, connects to a future you cannot see but can dimly imagine, a future where answers to tonight's questions finally arrive. The universe reveals its secrets slowly, rewarding patience and persistence, while withholding certainties that might make the quest seem complete. Tonight's discovery adds another chapter to a story that began when the first human looked up and wondered, a story that will continue long after we're gone, written by generations yet unborn who will remember this moment as the time when everything changed. The confirmation of extraterrestrial life, should the current findings withstand continued scrutiny, would constitute one of the most profound discoveries in human history, comparable to the Copernican revolution that displaced Earth from the cosmic center, or Darwin's theory that connected humanity to all other life through common descent. As you sink deeper into the comfort of your pillow, let's contemplate what such a discovery might mean for the way we understand ourselves, our world, and our place in the vast cosmic story. Religions have grappled with the possibility of extraterrestrial life for centuries, with responses ranging from firm denial to enthusiastic embrace. The medieval Christian philosopher Thomas Aquinas argued that God's omnipotence implied no limits on creation, leaving open the possibility of beings on other worlds. More recently, the Vatican Observatory has hosted conferences on astrobiology, with Catholic theologians expressing openness to extraterrestrial life as consistent with divine creative power. Other religious traditions have their own perspectives, from the Hindu cosmology that has always assumed countless inhabited worlds to the more Earth-centric views of some fundamentalist interpretations. The discovery of actual alien life would test these theological frameworks, demanding either accommodation or rejection of empirical evidence. Philosophers have long speculated about how confirmed alien life would affect human self-understanding. The principle of mediocrity, which holds that Earth and humanity occupy no privileged position in the cosmos, would receive powerful confirmation. We would know definitively that life is not unique to our planet, that the universe generates living systems through processes that operate across cosmic distances and timescales. This knowledge might inspire humility, a recognition that our species represents one experiment among many rather than the pinnacle of creation. Or it might inspire pride, a sense that humanity belongs to a cosmic community of life-bearing worlds, connected by shared biochemistry and perhaps shared destiny. The psychological impact on individuals would vary enormously depending on prior beliefs and temperament. Surveys consistently show that most people would react positively to news of extraterrestrial life, expressing excitement and curiosity rather than fear or despair. However, surveys cannot fully capture how people would respond to actual confirmed discovery rather than hypothetical scenarios. The abstraction of alien life in science fiction differs qualitatively from the concreteness of knowing that specific organisms exist on a specific world observable in the night sky. Some individuals might experience existential vertigo, a disorientation arising from the sudden expansion of their conceptual universe. Others might feel profound joy at finally knowing we are not alone. There's a fascinating historical parallel in the European encounter with the Americas, which forced dramatic revision of worldviews that had assumed all significant lands were already known. The discovery of entirely new continents populated by peoples unknown to European, Asian, or African civilizations challenged geographical, anthropological, and theological assumptions. researchers still argue about whether the Columbian encounter provides a useful analogy for extraterrestrial contact, with some noting important differences, while others emphasize structural similarities in how paradigm-shifting discoveries reshape human thought. The discovery might also reshape political and social structures in ways difficult to predict. Throughout history, external challenges and opportunities have sometimes unified previously divided groups, providing common cause that transcends parochial conflicts. The knowledge that humanity shares the cosmos with other life forms might foster a sense of planetary identity, an earthling consciousness that emphasizes commonalities over differences. International cooperation on space exploration might accelerate, as nations recognize that the quest to understand alien life requires resources and capabilities beyond any single country's reach. Alternatively, the discovery might intensify competition, with nations racing to establish contact or claim whatever advantages alien knowledge might confer. The scientific community would undergo its own transformation. Astrobiology, currently a relatively small field drawing from astronomy, biology, chemistry, and geology, would suddenly become central to scientific enterprise. Funding would flow toward efforts to confirm and characterize the discovery, creating new research positions and training programs. The questions that astrobiologists have pondered theoretically would become empirical, answerable through observation and experiment, rather than speculation and modeling. A new generation of scientists would grow up knowing that extraterrestrial life exists, their research agendas shaped by this fundamental fact, rather than treating it as an open question. You might wonder how the arts would respond to such epical news. Artists throughout history have drawn inspiration from scientific discoveries, translating technical findings into emotional and aesthetic experiences accessible to broader audiences. The discovery of alien life would provide endless material for painters, musicians, writers, and filmmakers, who would interpret the finding through countless creative lenses. Science fiction, which has long imagined this moment, would need to evolve beyond speculation into documentation, addressing the reality of alien life rather than merely its possibility. New genres might emerge, new modes of expression adequate to the new reality. The economic implications remain highly speculative but potentially significant. If alien life proves to be microbial or simple, the direct economic impact might be limited to scientific industries and educational materials. But even microbial alien life would demonstrate that the processes leading to biology operate throughout the cosmos, implying that more complex life likely exists elsewhere, even if not on this particular planet. Such knowledge might accelerate investment in space exploration and the technologies needed to reach other worlds, creating new industries and economic opportunities. If the discovery eventually leads to contact with intelligent beings, the economic transformations could be revolutionary, though predicting their nature exceeds any reasonable forecasting capability. For tonight, let these implications swirl gently through your drowsy awareness, not demanding resolution, but simply existing as possibilities that the future might bring. The universe has offered evidence that we might not be alone, evidence strong enough to merit serious attention even if not yet conclusive. How humanity responds to this evidence, how we adjust our institutions and beliefs and aspirations, remains unwritten history that you and everyone alive today will help shape through your reactions, your conversations, your choices. The discovery belongs to no single nation or group, but to the species as a whole, a gift of knowledge that arrives at a moment when humanity faces many challenges and needs all the perspective it can muster. The night embraces you as these thoughts settle into something between contemplation and dream, the boundary blurring as sleep approaches, and the boundaries between what is known and what is imagined become porous and permeable. As you drift closer to the threshold of sleep, the perspective widens from the specific planet and its biosignatures to the vaster context in which this discovery sits. You are a collection of atoms that somehow became aware of themselves, living on a rocky planet orbiting an ordinary star in an unremarkable galaxy among trillions of galaxies scattered across an observable universe 93 billion light-years across. The discovery of another world where atoms might have achieved similar self-awareness shrinks the apparent loneliness of existence while simultaneously emphasizing its magnificent improbability. Consider the chain of events that led to this moment. Roughly 13.8 billion years ago, the universe exploded into existence from a state of unimaginable density and temperature, expanding and cooling through phases that physics can describe, but human intuition cannot fully grasp. Within the first few minutes, hydrogen and helium nuclei formed from the primordial plasma, the raw material from which everything else would eventually be built. Hundreds of millions of years passed before the first stars ignited, fusing hydrogen into heavier elements that accumulated over stellar generations until enough complexity existed for rocky planets to form around later generation stars. Our sun formed roughly 4.6 billion years ago from a cloud of gas and dust enriched by countless stellar deaths. The calcium in your bones and the iron in your blood forged in the cores of stars that exploded before our solar system existed. Earth coalesced from the debris circling the young sun, its surface molten and hostile until cooling allowed oceans to form and chemistry to begin exploring the vast space of molecular possibilities. Somewhere in those primordial waters, or perhaps in hot springs or hydrothermal vents, molecules began replicating and competing and evolving, launching the biological adventure that would eventually produce creatures capable of building telescopes and wondering about alien life. The planet orbiting that distant K-type star presumably followed a similar cosmic trajectory. Its atoms forged in stellar furnaces, its surface shaped by geological processes, its chemistry eventually producing whatever life now maintains the atmospheric disequilibrium Webb detected. Two worlds, separated by light years of empty space, independently discovering how to sustain organized complexity against the universal tendency toward disorder and decay. The coincidence, if it is coincidence, speaks to something deep about the nature of reality, something that physics and chemistry alone cannot fully capture. There's a quirky philosophical tradition called cosmicism, associated with the writer H.P. Lovecraft, that emphasizes the insignificance of humanity against the vastness and indifference of the cosmos. Lovecraft imagined this realization as horrifying, a source of existential dread that undermined all human meaning and purpose. But the discovery of alien life suggests a different reading of cosmic vastness, one where the universe's immensity becomes not a source of horror, but of wonder at the creativity embedded in physical law. Matter, left to its own devices under the right conditions, organizes itself into patterns that observe and ponder and search for companionship across the light years. This seems less like cosmic horror than cosmic poetry. The search for extraterrestrial life connects to humanity's deepest motivations, the drives that have propelled exploration, science, art, and philosophy throughout our species' history. We want to understand where we came from and where we might be going. We want to know if the universe cares about us, or at least contains others who might care. We want context for our brief individual lives within some larger story that gives them meaning. The discovery of alien life wouldn't answer these questions definitively, but it would reshape the frameworks within which we pursue answers, providing new data points for the eternal human project of making sense of existence. You feel your breathing slow further as these cosmic perspectives wash over you, too vast for waking thought to hold firmly, but somehow appropriate for the liminal state between consciousness and dreams. The specific details of atmospheric spectroscopy and Bayesian probability estimates fade into background, replaced by the simpler, more profound realization that the universe might be inhabited by multiple experiments in awareness, multiple perspectives on the cosmic story, multiple voices in a conversation that has been ongoing since the first stars ignited and might continue until the last stars fade. Your place in this story is both infinitesimally small and infinitely significant. Small because the universe extends beyond comprehension in every direction, containing more stars than humans could count in countless lifetimes, more planets than grains of sand on all Earth's beaches, more possibilities than any mind could enumerate. Significant because you are here, now, aware, contemplating these possibilities with a consciousness that somehow emerged from unconscious matter and will eventually return to it. The atoms that compose you have participated in cosmic history for billions of years and will continue participating for billions more, cycling through stars and planets and perhaps other living things until the universe itself winds down into heat death unfathomable ages hence. The discovery we've traced tonight represents one moment in this vast story, a moment when one form of awareness detected evidence of another across distances that might never be physically crossed. Whether the detection proves correct or eventually joins the list of false alarms, the attempt matters. Humanity reached out with its instruments and found something worth investigating, something that suggests the universe's tendency to generate observers might be as fundamental as its tendency to generate stars and galaxies. We are not mere accidents, but expressions of cosmic creativity, and we might not be alone in that expression. The night grows quieter around you as these thoughts settle into the deeper layers of consciousness, no longer demanding attention, but simply present. like stars visible through a window that you notice without actively observing. Tomorrow will bring other concerns, other demands on your attention. But tonight, the universe has whispered a secret that will remain with you even when you've forgotten the specific words. Something lives out there, probably. Something looks at stars and wonders, possibly. Something shares this cosmic moment with us, perhaps. The thought is enough. The wonder is enough. The possibility is enough to transform the darkness from empty void into pregnant mystery, alive with implications that unfold across scales of space and time that dwarf human concerns, while somehow remaining relevant to them. The stars outside your window, if you have a window, shine with the same light that has traveled across the cosmos, carrying news of distant worlds. One of those stars, too faint to see with naked eyes but present nonetheless in the vast canopy of night, hosts a planet where something extraordinary might be happening right now as you prepare to surrender consciousness to the gentle tide of sleep. The journey we've taken tonight has carried you from the golden mirrors of a space telescope through layers of scientific evidence and philosophical implication, and now it's time to let the journey settle into the quieter rhythms that will carry you through the night. The atmospheric signatures that Webb detected, those telltale absorptions of oxygen and methane and water vapor, represent more than chemical data points. They represent the possibility of company in an otherwise silent universe, the suggestion that life's tendency to emerge and persist might be written into the very fabric of physical law. For billions of years, Earth seemed unique in its biological abundance, the only island of awareness in an ocean of dead matter and empty space. Tonight, that uniqueness appears less certain, the ocean perhaps dotted with other islands we're only now learning to see. You've learned how telescopes work, how they capture light and tease apart wavelengths to reveal molecular fingerprints invisible to unaided vision. You've traced the reasoning that transforms spectral data into probability estimates, the careful logic that weighs evidence and acknowledges uncertainty while drawing conclusions strong enough to reshape scientific priorities. You've contemplated what alien life might look like, from simple microbes to complex ecosystems, to perhaps even intelligent beings pondering the same questions we ponder. And you've considered what such discovery might mean for humanity's understanding of itself and its place in the cosmic story. The K-type star hosting this remarkable planet shines steadily across the light years, a nuclear furnace that has burned for 6 billion years and will burn for billions more. Around it, a world maintains atmospheric chemistry that shouldn't exist without ongoing replenishment, chemistry that on Earth we know to be maintained by living systems. The researchers who made this discovery have presented their evidence with appropriate caution, acknowledging the residual possibilities that something other than biology might explain their observations. But the probability calculations favor life, and favor it strongly enough that the scientific community has taken notice. What happens next unfolds on timescales that might exceed your individual life, but belong to the collective adventure of your species. More observations will refine our understanding, either strengthening the biological interpretation or revealing complications that demand alternative explanations. New telescopes will provide new capabilities, allowing questions that cannot currently be answered to yield their secrets. Perhaps within decades, perhaps within centuries, humanity will know definitively whether life exists on this world, and that knowledge will transform everything it touches. For tonight, though, certainty matters less than wonder. The universe has offered a gift, a candidate world for extraterrestrial life, compelling enough to merit sustained attention and serious investigation. Whether the gift proves to contain what it promises or ultimately disappoints, the offering itself demonstrates something remarkable about the cosmos we inhabit. It generates worlds where life might flourish, worlds separated by distances that seem insurmountable, yet connected by the light that carries information across the void. Your eyelids grow heavier now, the detailed thoughts that filled earlier sections dissolving into simpler impressions and feelings. The golden hexagonal mirror of Webb floats in your imagination, catching starlight from across the cosmos and translating it into data that human minds can interpret. The distant planet exists in that imagination too, not as a collection of spectral measurements, but as a place, somewhere real, where alien seasons turn and alien weather patterns develop, and perhaps alien organisms go about their alien business, unaware that distant observers have detected their chemical signatures. The boundary between waking and sleeping grows porous, and the hard edges of fact and speculation blur into something softer and more dreamlike. The discovery we've explored tonight becomes less a scientific finding than a feeling, a sense of cosmic companionship that doesn't require certainty to provide comfort. The universe seems less empty than it did before you started listening, less indifferent, less vast in the lonely sense of the word. Other worlds exist out there, and at least one of them appears to be doing something interesting with the matter and energy available to it. Let that thought carry you now, a gentle current flowing toward the shores of sleep. The atoms that compose your body, forged in ancient stars and organized by billions of years of evolution into patterns capable of contemplation, settle into the relaxed configurations of rest. Your breathing slows to match the unhurried rhythm of the universe itself, expanding and contracting like the cosmic breath that began with the Big Bang and continues through every moment of existence. The stars outside remain, whether you see them or not, burning steadily through the night as they have burned through countless nights before and will burn through countless nights to come. Among them, somewhere, a planet maintains the chemistry of life, its atmosphere whispering secrets that we've only begun to hear. The conversation between worlds has started, carried on beams of light that need no response to complete their journey. Sleep now, and let the universe hold its mysteries while you rest. The discovery will still be there tomorrow, and the questions it raises will occupy human minds for generations yet unborn. Your role tonight has been to witness, to contemplate, to feel the weight and wonder of what we've learned. That witnessing matters, connects you to the cosmic story in ways that transcend your individual existence. The night deepens, soft and welcoming, and the stars keep their vigil as they always have. Somewhere out there, perhaps, other eyes close in other nights. Other minds drift toward other dreams. Other beings rest in the confidence that they are not alone in the vast dark. We cannot know this for certain, not yet, but we can imagine it. And imagination is its own form of companionship. Sweet dreams await, full of golden mirrors and distant worlds, of atmospheres that breathe with life and stars that cradle possibilities beyond counting. Let them come, these dreams, carrying you through the hours until morning returns with its ordinary demands. The universe whispers its lullaby, and you have heard it. And so the journey settles into stillness, the way all journeys eventually must. The scientific details that filled the earlier hours have dissolved now into something simpler and more essential, a feeling rather than a fact, a presence rather than a proof. The distant world with its oxygen and methane and water vapor exists out there whether you think about it or not, maintaining its chemical mysteries while you rest. Your body has grown heavy with the pleasant weight of approaching sleep, your thoughts no longer racing, but drifting like leaves on a slow stream. The universe remains as vast as ever, but its vastness feels less empty tonight, populated by possibilities that transform cold statistics into warm companionship. Somewhere, perhaps, other beings share this moment with you, though separated by distances that light itself needs years to cross. The breath comes slow and easy now, each exhale releasing the day's accumulated concerns, each inhale drawing in the quiet peace of night. The stars wheel overhead in their ancient patterns, indifferent to human timescales, yet somehow reassuring in their constancy. They were here before you were born and will remain long after, silent witnesses to all the small dramas of consciousness that flicker briefly against the cosmic backdrop. Let the last threads of wakefulness loosen their grip. The discovery we explored tonight will wait for you, preserved in memory and in the ongoing work of scientists who will continue the investigation while you sleep. Your only task now is rest, is renewal, is surrender to the gentle darkness that cradles all living things at the end of their waking hours. The universe dreams perhaps, and you dream with it. Sleep well.